Hello.
Sir, good afternoon. Good evening, sir. Welcome to our FDP, sir. Yes, sir.
We can start.
Yes, sir. Yes, sir. Please, sir. Yes, sir.
Good evening, everyone. I am Nakshandil Kumaran, principal of this institution. I welcome all the participants and organizers for this ATAL FTP. I congratulate the organizers and also the participants for selecting a very relevant topic of today. So consequently, in the month of December, Tamil Nadu is facing a lot of threats from cyclones. So we are in a condition to understand this position and subsequent consequences in the natural disasters. So it is a very relevant topic. I once again congratulate all the participants and organizers for having this program. I wish you all success. Hopefully, I will join whenever time permits. I thank all the resource persons for helping us, and we also thank the ATAL FTP for sponsoring this program. So once again, I congratulate every one of you and thank you. I may be please permitted to inaugurate this function and say you wish you all success. Thank you.
Thank you, sir. Thank you so much, sir. Thank you.
Please proceed. Thank you.
Thank you, sir. Thank you, sir. Good evening, respected dignitaries, esteemed guests, faculty members, and my dear participants. On behalf of SSM Institute of Engineering and Technology, it's my privilege to welcome you all to the inaugural session of the AST sponsored 6 days online FDP program on resilient infrastructure for cyclone prone areas. It's our honor for our faculty of Civil Engineering Department, SSM Institute of Engineering Technology, Dindigul, to host this 1 week faculty program. This is our third time conducting this AST sponsored ATAL FDP. As we all know, cyclones are natural disasters that frequently impact coastal regions, causing damage to life, properties, and infrastructure. The increasing frequency and intensity of these events make it is necessary that we prioritize the development of infrastructure that can be withstand with the natural forces. Traditionally, infrastructure designs often prove inadequate in the face of cyclonic winds and heavy rainfall. Bridges, road, buildings, and communications network can be easily destroyed, causing disturbance to the essential services. The economic losses and human suffering caused by the such damage are also very huge. Therefore, we need to move beyond simply reacting to disaster and instead proactively building infrastructure that can withstand them. That involves incorporating advanced materials, innovative designs, and robust construction techniques. That's why we proposed on this topic for this FDP. So we have submitted the proposal and we are fortunate enough to get this approval. We are thankful to our principal sir, Dr. D. Sendil Kumaran, on his support and advice we could be able to submit the proposal. We are thankful to all our participants for registering this particular program. We are thankful nearly 220 plus participants across 13 states in our registration statistics. We have got very good speakers across the national and a few of them with international repute. We have totally 13 speakers. I hope would be very interesting and definitely we will be benefited through this FDP. To set this stage for today's proceeding, it may honor to introduce our college a small video and related to resilient infrastructure for cyclone prone areas. Thank you. this small introduction about our college, I would like to start our FDP session. The first section handled by Dr. Umarnath Umayan, L&T Geotechnical Manager, L&T Chennai. Good evening, everyone. It's my great pleasure to introduce Dr. Umarnath Umayan, the resource person for today's first session. He is currently the geotechnical manager R&D and L&T construction with over 8.5 years of experience in geotechnical research, consultancy and project execution. He's graciously accepted our invitation at the last minute despite his busy schedule. We sincerely thank him for making time to be with us and share his valuable knowledge and experience. He holds a bachelor degree in civil engineering from Tyagaraja College of Engineering, followed by master degree in soil mechanics and foundation engineering from the College of Engineering Gindi. He earned his PhD in geotechnical engineering from NIT Trichy. On the professional form, Dr. Umanath has an impressive and dynamic career. His career spans various roles. He started as a civil engineer and later contributed as professor. Currently, he serves as the manager of geotechnical research and development at L&T Chennai. Sar has worked on several major projects, including the Chennai Metro and Skyda Refinery, contributing innovative solution in ground improvement and soil testing techniques. Beyond his impressive professional achievement, he is a recipient the best PhD thesis award from Indian Geotechnical Society. We are truly grateful for his willingness to join us on such short notice. We are looking forward to hear his proximity and resilient infrastructure for cyclone-prone areas. Please join me in giving a warm virtual welcome to Dr. Umanath Umayan. Sir, I kindly invite you to share your screen and begin the session. Welcome you, sir. Now the time is yours. Thank you, sir.
இல்ல இப்ப எனக்கு மைக் மட்டும்
yes sir, yes sir. Now it's working, sir.
மைக் ஒர்க் ஆகுது, நான் ஷேரிங் ஆப்ஷன் வரல.
சார் நீங்க இப்ப நம்ம பிரசன்டர் பண்ணிட்டேன் சார்.
ஓகே, இப்ப நான் ஓபன் பண்ண உங்களுக்கு இப்ப தெரியுதுங்களா? என்னோட ஸ்லைட் தெரியுதுங்களா?
இன்னும் ஓபன் நீங்க ஷேர் கொடுங்க சார் ப்ளீஸ் சார்.
இல்ல எனக்கு ஷேரிங் ஆப்ஷன் ஓகே வந்துருச்சு மேம். தேங்க்யூ.
ஓகே சார், தேங்க்யூ சார், தேங்க்யூ.
Okay, am I visible and audible?
Yes sir, yes sir.
Yeah, fine. Thank you. So good evening to everybody. This is Dr. Umanath. I would like to thank HOD Civil Engineering of SSN College for the overwhelming introduction. So let us delve into the topic straight away. So I don't want to waste any time on it. Then, so the topic I took is geotechnical considerations for cyclone resisting structures. So before that, I have a two consideration to join in the geotechnical consideration. Just one is, I am okay with in-person presentation rather than this virtual presentation, so that I can see the people's reaction for the point that I am taking out, so that I can change the way of teaching or change the way of lecturing. So that consideration is for me. And second consideration is obviously the after tiring your working day, you are actually sitting in your home or any working place after 6:30 is very difficult to sit and hear the lecture for another 1 hour or 1.5 hours. So just take all those consideration away. Let us start our geotechnical consideration for the cyclone resisting structures first. So since it's your first day of this FDP, I think, I hope, people from other domains like environmental structural engineering will give all of their considerations. So, but this, since it's our first presentation, we should know about what is cyclone, what is the behavior of cyclones, what is the characteristics of the cyclone. So then only we can say what is the impact on the structures, on which domain we have to consider the specific characteristics and all. So the first definition of the cyclone is a large scale atmospheric systems. It starts from the central positions with the low pressures, so that is called I. So surrounded by the wind patterns, that is called eye walls. I will show, I mean, I will explain those things. So this intense weather phenomena causes significant damage due to high winds, heavy rainfall, and storm surges. So the content or the basic is windfall, but the byproduct of that cyclone is actually heavily induced by high winds, heavy rainfall, and storm surges. Here I could say that these three phenomena actually damages the most of the structures, as well as the geotechnical aspects. We have to think of all the three parts. So this is the characteristics of the cyclone, a basic cyclone. Let me start with the formation dissipations. So how it starts, how it's forming, how it is dissipating. So mostly the cyclone happens in the tropical oceans. Tropical oceans means where your temperature is mostly around more than 26 degrees. So where your temperature is more, there will be evaporation of air. So I mean that the pressure of air will actually go to the upside or to the atmosphere, where your pressure will be very low. Where your low pressure happens to the top of your tropical oceans. So there creates your that derives the heat and moisture from the tropical oceans. So it started to form as a total cyclone, and it move around and dissipates over the cool area, wherever it moves. If there is a cool places, so obviously you may expect a huge rainfall. So what it gives a heavy rainfall. You just imagine, maximum it can give a 500 rainfall in a, so that definitely will make a flooding and landslides. So without a doubt, and a storm surges. So it is actually rise in the sea level. So while you have a very forceful and a heavy windfall, I mean wind force, definitely it will actually move your waves, that will make your sea level to rise to a bit. So definitely that will be another catastrophic effect. Then the low pressure, as I mentioned earlier, it will be create a low pressure at the center. It is called I, and it's surrounded by the eye wall. That is the reason, it will cause us the intense wind and rainfall. So that is the important point. And high wind speed. So it actually make a 250 km per hour wind at the maximum. So just imagine the 250 km per hour wind attacks your structure or any other material. What will happen to that? So this is the basic characteristics. And the size and duration, and it actually tends up to hundreds of kilometers of span, and it lasting around several days, and it can get intense in 24 to 48 hours. That is the peak period that we actually get into the news. So your no cyclone is going to get intense. It's going to give the rainfall amount. So that kind of warning that we are getting, right? So that is a part of indensation of the particular cyclone. So fine. Now let us go to the historical damage to the structures. I mean, I cannot go beyond, more than 50 years back. Just imagine, for the last 50 years alone, India has faced 117 cyclones in the history, and it took around 40,000 lives to the various cyclones. Here, right side, you can see. Wait a minute, I can. Yes. So these are all the damages caused by the recent Bengal cyclone. So mostly this is Chennai, and this is Kadalur district, and some of the places I have taken from the internet only. This is the recent, but want to show you the recent damages created by the Bengal cyclones. This is the name of the cyclones has affected India in the past 1 decade. Starts from 2013 to 2024. Could see that. So this is the fatalities it caused, and this is the economic losses caused by this cyclones. So just imagine. So this is not easy to you cannot take it easy of the cyclone. It actually make a lot of economical losses. Fine. So what are the impact of the cyclones? Let us see stage by stage. It is actually make a structural damage. like high winds and flying debris. I mean, you can see a lot of videos in the YouTubes, and you can see in the lot of newspapers, news channels. There is a heavy wind actually make the lot of debris to fly, and that kind of debris can destroy any kind of buildings. Buildings, bridges are absolutely infrastructures. That is the main damage of the structural thing. And then flooding. Because of the heavy wind, as I mentioned, heavy wind and heavy rainfall, obviously there will be a flooding. So flooding with the 500 of rainfall will make definitely a huge flooding, as well as the storm surges. This can be lead to a widespread flooding. This flooding definitely will actually make a lot of damage to your existing structures. And erosion. Erosion is nothing but scours and erosion of the existing structures, and the soil surrounding your structures make your structure out of lateral support. So the coastal areas experience significant erosion due to wave action and storm surges. So these are all erosion part, and human and economic losses. So cyclones can result in a loss of life, displacement of communities, and economic devastations. So above 3 points, structural damages, floodings, and erosion, these 3 points can be a replaceable one. You can easily replace your structures, any bridges and anything. But just fourth point is a unreplaceable. It took human lives and economic losses. These are all very devastating effect of the cyclones. So by saying that, the basic introduction of the cyclone, what is its characteristics, what is its impact, let us just go to the technical part. So you may see like what is the geotechnical relevance to the cyclone part, because if you hear the term called the cyclone, probably everybody would think like, cyclone will have a high wind force, heavy rainfall, it will damage your structure. But nobody thought it also affect your subsurface. That is called foundation or geotechnical aspect. So I'm just presenting here what are the challenges imposed by the cyclones on the geotechnical design. Starts with the uplift forces on the foundation due to heavy winds. In the right side picture, you could see that a transmission tower resting on a piles, single pile. Here I have mentioned a single pile, but there will be a pile groups also. But just consider, due to this heavy wind, this I mean, burden for one more time. Let me take the laser. Yes. Fine. Because of this heavy wind, the transmission tower gets laterally displaced. Because of this lateral displacement, obviously your piles, actually one side it is getting settled, another side is getting heaved, because this side will actually affected by the compression, this side is actually affected by the tension. So this kind of uplift force acting on the foundation, which is, if we are not designed for that uplift force, obviously your transmission tower will fail. Right? Fine. Then the second is an important point called liquefaction of soils during heavy rainfall. I don't think I'm not sure about the domain of attendees. Probably most of the people are coming from the structural background, don't understand the terminology called liquefaction. This is a specific terminology we use in the geotechnical. So let me dwell more detail on the liquefaction, because I want everybody to understand what is the very important challenge posed by the cyclones. That is called liquefaction. So liquefaction of soils during heavy rainfall. Obviously, the heavy wind and cyclone gives the heavy rainfall here. So because of the rainfall, what will happen? So the first thing is liquefaction. Then scour and erosion. Obviously, because of the high force running water in the rivers, streams, and coastal areas, and high force, obviously scour and erosion will happen in the around foundation. You can see in this picture. So this is the foundation of existing bridge. Because of the running water erosion as well as the heavy wind erosion, your foundation surrounding soil has been exposed. Your foundation has exposed. So this is loss of lateral strength. Definitely, it will get failed. Then fourth point is lateral forces from wind pressure and storm surges. Obviously, any kind of structure which is not considered the lateral forces, if you take it a tall structure or any kind of even a superstructures, that will impose your uplift force or lateral force to your foundation system. So these 4 points you have to take as a challenges imposed by the cyclones in the geotechnical aspects, right? So let us see one by one. First, so to know about what is the impact on the geotechnical aspects, let go back to the types of soil. So obviously people might know what is the types of soil. Basically, let me brush up the basics. So the soils can be defined in the category of coarse grain soil as well as fine grain soil. Obviously, the soils or any particles which is retained on 4.75 mm, that is more than 4.75 mm particle sizes, it is called the gravel. So we don't bother about that. Geotechnical engineering is always about which is passing 4.75 mm, which means I mean soil mechanics, not geotechnical engineering. So soil mechanics, we only bother about the soil particles which is passing 4.75 mm. So if 4.75 mm to 75 micron, it is called coarse grain soils. So here the shear strength is defined by friction angle. So obviously most of the particles in this region, I could say it is a sandy soil. This sandy soil can be bifurcated into many names. Sandy soil, clay soil, poorly graded sand, and well-graded sand, silty sand, clay sand. This kind of lot of bifurcation is there. But as of now, let me give a broader classification. This much, if you know, that is good enough. So the shear strength defined by the friction angle. Here is an important point. So since you are mostly from the structural background, so you know about concrete and most of the steel kind of things. So the obviously concrete is good in compression, but very bad in the tension. As in the same case, if you take a steel is very good in tension, it's bad in compression, which means that material on which force it will fail. Concrete will fail by the compressive force, which means axial load, and your reinforcement will fail in the tensile load. That's all. In the same way, soil, any type of soil, if you take, it will fail in the shear failure, which means a horizontal movement between the soil particles. So it will create no stress, then the soil gets failed beyond one certain point. So this up to what limit any particular of soil type can withstand that shear force, it's called shear strength. So the contribution of the shear strength of the particular soil is based on mostly two parameters. One is friction angle, another one is cohesion. So this coarse grain soil is actually governed by the friction angle. Symbolically, you may say it is a pi value, and generally known as a sandy soil. Like I already mentioned that. Then there's a fine grain soil. So particle size is less than 75 micron. It is called actually clays. I mean, fine grain soil. The shear strength defined by cohesion. As I mentioned earlier, there are two parameters that governs the shear strength. The coarse grain soil taken by the friction angle and fine grain soils taken by the cohesion. So the particles which is less than 2 micron is called clay. So if you consider 75 micron to 2 micron, that is called silt, and from below 2 micron, it is called clay. So you may I mean, sandy soil has its own properties, own way of behavior. The clay soils has its own way of behavior, own way of properties. But the particle sizes, which is 75 micron to 2 micron, is having a very there is no distinctive way of behavior. Actually, it will have both the properties of sand as well as the clay. So with this basic introduction of the type of soil, let us jump into the behavior under cyclic loading. Why the cyclic loading? Cyclic loading can happen by many criteria. For example, if you take a earthquake actually gives the major contribution to the cyclic loading to the soil. But in the case of cyclone, if you take a cyclone, yes, cyclones also can give a cyclic loading to the soil, which means your movement of the heavy wind actually take a toll, and it actually stops at some position, and then it will come. So this kind of on and off kind of movement, it actually create a cyclic load. And obviously, with the heavy rainfall, any rivers or any running streams or any coastal, that will create a waveform that will actually attack your structure with the on and off movement, which means hitting the structure, going back, hitting the structure, going back. That is the process of waves, right? That's how the wave actually moves around. Clear? So actually, people are following me, right? Hello?
Yes, they are listening, sir. Yes, sir.
Yeah, fine.
Yes, sir.
Okay, fine. I just wanted to get a confirmation, that's all.
Okay.
Fine. So these kind of cyclic loading actually happening because, as I mentioned, there are a lot of scenarios that create cyclic loading, like liquefaction. I mean, sorry, say like earthquake, as well as this kind of cyclone kind of things. And obviously, there is a vehicular movement, blasting. No, these are all wherever which whatever the action may be, if it creates a surface wave or body waves kind of motion, it experts the energy into the soil that will create a cyclic loading. right? So obviously, if any movement is there, now that will actually follow the surface wave as well as the body waves movement. As you know, the body waves or shear waves as well as the compressive waves, surface waves called Rayleigh waves and Love waves. These four types of wave definitely will be created by the cyclic loading. So for this loading, how our soils actually gets behaves under kind of cyclic loading. That is the point we are going to see here. So fine. So the cyclic loading can significantly alter the mechanical properties of soil, leading to phenomena such as liquefaction, settlement, and strength degradation. Right. So the cyclic loading caused by cyclones because of the random cyclic loading. So this behavior of the soil again depends on five parameters. One is soil type, right? So if it is a well packed, just imagine your soil is well packed, having a good density, and your soil is having coarse grain soil. Shear strength is governed by your friction. It is well compacted, well packed. What will happen? Any type of cyclic loading happens, definitely you don't act, I mean, to at least some extent, it don't actually get affected. And the same way, if water content is present in the subsurface, if it is a sandy soil, because of the cyclic loading, the pore water pressure development will be development will be more, but dissipation will be very fast. But in the case of clay soil, the dissipation will be very slow. That will lead to the settlement for the longer period. So this kind of scenario will happen only because of the type of soil. Then come back to the, let us see the density part. If your soil is properly dense, properly compacted, which means it around 90 to 100% of its maximum rate density. What will happen? Any type of cyclic loading happens, the soil or any the structure, substructure actually withstand against that. But if your soil is poorly packed, the density is very low, like 60 to 70% of the OMD. Even if you take the relative density, if it is 60 to 70% only, so that will be categorized in the medium dense sand. So such a density will affect, by the action of cyclic loading, a low dense material definitely will get affected. In the case of high dense soil, there it will get affected, but up to some extent it will actually resist the cyclic loading. Then degree of compaction, as I mentioned, density and degree of compaction comes to the same bracket. Then magnitude and frequency of the loading. So magnitude, as we are here, we mostly consider 7.5 magnitude as the standard magnitude. If goes beyond that, is definitely it is very huge magnitude. But if I can see, you can see the Richter scale measurements of every earthquake in the news. That is called magnitude. So then the frequency of loading. Frequency of loading means it's a meter. Cycles per second. How many cycles per second? So every material has its own natural frequency. Take it from the soil to the structure, concrete, beam. Every material has its own natural frequency, right? So now a particular material, for example, let us take a foundation that is having a natural frequency of 2 Hz. Okay. Now I'm actually earthquake is happening or any cyclic loading is happening. There the frequency is also 2 Hz, means the natural frequency and the current frequency are both are similar. What will happen? The resonance will happen. A structural get the resonance from the upcoming cyclic, so the failure will be very huge, right? So but if a frequency of the natural frequency of the particular structure is very high, it is get like 20 Hz or the 100 Hz. In that case, even your cyclic loadings apply in the 2 Hz of frequency, definitely that won't affect your structure. That is why usually people ask to construct a building with a natural frequency of more than 10 Hz, because natural earthquake or any kind of cyclic loading will not go beyond 5 Hz, right? Then confining pressure. Confining pressure is nothing but how much surrounding soil is getting giving a confining pressure. It's all around pressure happening onto your particular structure. If you take a foundation or any substructure, it is all defined by your confining pressure. If there is no confining pressure means all around pressure acting at a particular point. Just imagine if your surrounding soil is a very soft soil. In the case of clay, it's a soft soil, or in the sandy soil, it is a loose condition soil. The pressure that exerted by the confined soil, if it is loose, then the high chances of failure under cyclic loading is there. But in the same case, the surrounding soil is a hard state, fairly hard state, and tightly packed, high compacted soil, the confining pressures given by the soil is very huge, right? So obviously, in the same way, the level of the foundation, confining pressure always, I mean, also taken the overburden pressure also. The pressure mean overburden pressure means at from the so depth from the surface as well as the unit weight of the soil. So gamma into H. So these kind of confinement actually gives the resistance against your cyclic loading. So these 5 points actually make your soil behave differently based on the cyclic loading, right? Now, coming back to the type of soil, how it actually behaves under cyclic loading, let us quickly go through. So if it is a sandy or granular soil, what happened? Liquefaction definitely will happen because sandy soil is a more prone to liquefaction. So because of the liquefaction, it loses strength. If any soil loses strength, what will happen? Any structure resting on such a soil definitely will settle or fail. Finish. That's all. Then settlement. Obviously, if soil is a loose condition, in the case of sandy soil, obviously a immediate settlement will happen. As we all know that sandy soil is a immediate settlement, the first degree settlement. If it is a clay soil, that will get a plastic settlement, creep settlement. But in the case of sandy soil, if your soil is in the loose condition, it is settled. If your soil is in the high density or highly packed, there is a chance of dilatation. Dilatation means decrease in your density. Let us put it in that way, decrease in the density. Then pore pressure buildup. Since it is your sandy soil, your voids will be more. The voids will be filled with the water. That water actually takes a lot of pressure from the cyclic loading. So that the pore water started to take more load or more pressure than the surrounding particles, which will lead the pore pressure development. So your effective stress is nothing but a total stress minus pore water pressure. Just imagine effective stress is equal to total stress minus pore water pressure, right? So if your pore water pressure started to increase or build up, it needs some dissipation way. But in the case of cyclic load imposed by the cyclone, there is no chance for water to coming out of your any pores. So the pore water pressure is developing and it's not able to dissipate. This is the condition. So in that case, water is not compressible. Water is not incompressible medium. So your soil particles get compressed at the bottom level and your water is getting more and more load, more and more pressure is not able to come out. Now in this case, the pore pressure increment, which is equivalent to, it will come at some point. So effective pressure is equal to total pressure minus pore pressure. The total pressure is equal to, I mean, the pore pressure will come equal to the total pressure. Obviously, then will what happen? So the effective pressure is equal to pore pressure. Then your total soil will lose all your strength. So that is the criteria. So once the soil loses all its strength, only waters take the load. Now what will happen? Obviously, your structure gets failed. So then the same case, if it is a clay or cohesive soils. So first, what will happen? The cyclic degradation. So gradual reduction in the stiffness and strength. Unless sandy soil, clay soil has its cohesive nature. So if you want to degrade the clay soil means you have to attack the cohesive nature. So the cohesive nature contributes more in the stiffness and strength here. So due to this cyclic loading, what will happen? A gradual reduction in the stiffness and strength will happen. Hence, the soil fails. But in the case of sand, the failure is very immediate. But in the case of clay and cohesive soil, the failure is a time prolonged one. Then pore water pressure dissipation. As I mentioned earlier, clay soil have a very less voids. The generation of pore water pressure itself actually very difficult for that. But still, the dissipation gets very take a lot of time, prolonged one. So the settlement will take its own time. For example, if a cyclic load attacks at the point of a clay soil today means the settlement may happen at 1 year after attacking. Just imagine if any cyclic load attacks on the clay soil by January of 2025, the after effect of settlement due to this pore water dissipation may happen at the January of 2026 also. So that is the problem with the clay soil. In one way, sandy soil actually giving us a indication I'm going to fail. Okay, I can make a remedial thing and all. But in the case of clay soil, don't give any indication. That is the problem with the clay soil. You cannot actually expect when it will get failed or something. So a proper design needs to be done for the clay and cohesive soils, right? Then Then the plastic deformation. As I mentioned earlier, clay soil have a later deformation, but it's called a permanent deformation. Once it's failed, definitely it won't get back to that position. So that is a plastic deformation. Then obviously silt and intermediate soils. So the previous slides we have seen silt has its both the properties of clay and sand. So obviously it have an intermediate behavior of sand and clay. It may sometimes go liquefaction if the sandy proportion is more. It may go to the cyclic degradation if the clay proportion is more. So that is what I have mentioned here. Undergo liquefaction and clay degradation based upon how much clay present in that particular silty nature. Okay, right. So let us, as of now, we have seen what are the type of soils, what are the behavior under cyclic loading. As I promised earlier, I am going to explain more about the liquefaction factor here because this is the point that most of the structural background people doesn't aware of that, right? Fine. So this is the liquefaction. Just you can see the left side. This is a soil block. Not block means don't consider as a brick kind of block. It is a soil, underground soil. Just consider, saturated granular layer. So here I'm going to give a cyclic shear load, which means the soil will get move opposite direction with the adjacent layer, right? So I'm going to experience this saturated granular going to experience a cyclic shear load to and fro in this movement, right? So what will happen here? You can see this picture where this is actually give the grains, sand grains, and this blue color indicates the pore water. So the effective stress is nothing but effective stress on the soil particles, which means whatever stress acting on the particular soil block, the pressure will be taken care by both the medium, which means soil grains as well as pore water. The stress will be equally shared between these two. So the effective stress is actually acting at the interface of the soil grains as well as the water. This is called effective stress. So this is the before liquefaction. This is how the soil particles gets a contact and the pore water, how it is actually contribute to the effective stress. Now, after liquefaction, what will happen? Due to this cyclic movement, the soil particles started to rearrange themselves. So it started to compress since water started to take the load, and obviously the water needs to be go out. It will actually looking for the dissipation point. If there is a no dissipation, what will happen? The water started to take more load and soil particles started to rearrange to this rearrange. Here there is a lot of gap between the particles to particles. The most of the gaps will be taken and covered by the water. So here the pressure taken by the water will be more than the soil particles. So that creates the problem. So water pressure will be more, the soil will not take any load. So whatever the structure constructed over any kind of liquefaction potential soil, if any liquefaction happens, so soil particle will not take any load, only water will take every load. What will happen if water takes all the load? Obviously your any structure constructed over that kind of material will settle or will float. That's all. So this is the basic idea of liquefaction. I hope you understand, right? So you can see what I have written here. Soil particles are floating due to increasing pore water pressure. Sign. So these are the words that I have mentioned. No, soil is saturated and filled with water between the voids. Yes, it is true. During a strong cyclic load, these waves will compress the soil strata. Yes, during the cyclic load, all the soil particles try to compress each other because of this wave action. So due to the compressive force exerted by the earthquake waves, loose soil try to densify, obviously. First, the waves try to compress the water present in the voids. This is the very common thing. Whatever load happens, water try to take the first load. But if there is a chance of water to dissipate, so the water try to move away. It try to move away, then automatically your soil takes the more load. But in the case of cyclic load, there is no way of dissipation for your water. So this is the problem here. So the waves try to compress the water present in the voids. So this is the point. So water is an incompressible medium, so it won't get compression. So it can only try to escape from the voids when the force is acting. And this is the another explanation, self-explanatory picture. So the A is actually having a loose sand over the groundwater level. There is a structure here. In the B, there is a seismic load acting on that. So what will happen? The soil particles try to rearrange. Water tried to move away, but it doesn't have any opening to go away. Here, the residual excess water pore pressures happen. So all the load has been taken by the water now. There is no part of soil particles to withstand the structure, so obviously your structures gets failed. So this is the simple self-explanatory picture here. So in the words we can see here, water presence in the voids cannot be escaped easily due to its concealment inside the soil, right? Then pore pressure increases and reduces the shear strength, results in the reduction in the effective strength. So I forgot to put in the equation. So effective stress is equal to total stress minus pore water pressure. Just imagine pore water pressure increase and increase. Obviously, it at one some point total stress and pore water pressure will actually come to the equal. So it will be zero. So effective stress will be zero, right? So once effective stress is zero means there is no strength available in the soil. So that is how the failure happens. At one stage, pore pressure exceeds the effective stress also. Shear strength becomes zero and soil liquefies. And now, here the effects of liquefaction on the foundation. So, as of now, we have discussed what is liquefaction, what is the phenomena called liquefaction, how it is actually generates. Now, we will see what is the effects of liquefaction on the foundation. Excuse me. Fine. There are four major effects on the foundation. One is uplifting of the structures, right? So once the soil gets liquefaction, obviously there will be a buoyancy effect. If your structure is a very huge or high-rise building, there is a possibility of settlement. But if your structure is very light-weighted, no very lightweight or featherweight structure means the water buoyancy will happen. In that case, the uplift of the structure may also happen, kind of. So this is very common along underground structures. Any structure that buried underground, like pipelines or any manholes, such a kind of structures, it will get uplifted because of the buoyancy effect of the liquefaction, right? Then tilting of the foundation. Liquefaction leads to settlement of a shallow foundations, which makes structures to deform and induce damage. And lateral spreading. This is happen only nearby the water stream area. If there is a nearby water basin, river basin, or any hilly region, there is a particular layer which is in the slopey strata. That part alone get lateral spreading that will damage the structure over that lateral spreading area. Then buckling of soils. This is a very important thing, and I will explain with the picture in the coming slides, right? Now see one, go one by one. First is uplifting of structures. So this is buried structures will undergo flotation and lead to damage, impose upward buoyant forces on the structure resting over it. As I clearly explained this portion actually, right? So you can see this picture here. Here the confined water trying to find the way out. Once it is find the way out, so all the water presence in this layer will actually join with the groundwater level. So here overall covered by the water will give the buoyancy effect to your structure. If a structure is good enough or strong enough or way enough to counteract your buoyancy effect, it will actually withstand. But if if your structure is very light structure, lightly loaded structure means definitely it will have this kind of uplift effect. So this is actually making lot of damage to the underground buried pipelines. The pipelines may be water pipelines, oil pipelines, even no electrical line pipelines, broadband pipelines, whatever buried structures. So this will create a lot of damage to the underground structures, right? Then tilting of foundation. This is a real-time picture in the Japan as well as this is taken in America. So tilting of the foundation. As I mentioned earlier, this kind of liquefaction will give a differential settlement. At one point, there is a stiff, your soil may have a very stiffer medium. In another side, you may have a very lesser stiffer medium. In this kind of liquefaction, reduces the shear stress at one side of the building means what will happen? That kind of tilting of the foundation may happen because of the buoyancy. You can take the example of here also. you can see the one side settlement happening because the water tried to go away at the one direction. If it is actually moves around all the direction, means definitely the foundation may settle uniformly, but we cannot predict, right? So where there is a small gap is there, water try to come out. This kind of failure make your foundation to tilt. This tilting of foundation will lead to a huge failure of your superstructure, even if it is in a 23, 30, 30 to 40 story buildings. Then lateral spreading. Fine. This is the finite lateral displacement of gently sloping ground. As I mentioned, this is the gently where your slope is very gentle and due to the pore pressure buildup or liquefaction in a shallow underlying deposit during an earthquake. Just imagine there is a layer which is having a very small thickness like 300 to 400 and that is in the gentle slope. So due to the pore pressure, that particular portion alone actually like a piece of cake, it will come out of your subsequent stratification. That particular portion of 300 gets failed called lateral spreading. So it causes damage to the foundation of the buildings, pipelines and railway lines and causes shaking it at piles due to the lateral loading. So this is because of the lateral loads. Then magnitude of this lateral deformation depends on the slope of the ground and the density of the subsoil and earthquake magnitude. If I ask you a question, if my slope is very steep, what will happen? Definitely the fail will happen. Fail will be more. Failure will be more. Chances of failure. But if my slope is very gentle, it's like 1 is to 1.5 kind of slope means that's a less chance of lateral spreading. So that is the point you have to note down here. Obviously, density will play a major role here, and earthquake magnitude, obviously, even if it is a 1 is to 2, 1 is to 1 is to 1.5 slope also get failed if your magnitude is more, which means more than 8 or 8.5. So these are all the factors that governing the lateral spreading damages. Then buckling of pile, that is very important or fascinating thing. Just imagine, I'm just read out these points. Liquefiable layer loses its strength during strong motion, obviously, as we have discussed that point earlier. Then pile move in opposite direction above and below the bottommost non-liquefied layer. Okay, then induced buckling of piles and leads to damage to the superstructure. Just here and you should understand the possibility of liquefaction potential of the soil at various stratified layers, right? Because as you know that soil is not uniformly homogeneous material. It may have a stratification up to 2 meter or 3 meter. There must be a different type of soil layer, and 2 to 4 meter there would be a different type of soil layer, and 4 to 5 or 4 to 6 you cannot expect. Soil is such a kind of material which is having a you know a proper diversity. It is not like a concrete or steel or any kind of structures, because those are all man-made materials. If you want to construct a building with M30 concrete, yeah, you can make a M30 concrete because you have all the data to create a M30. It will give a strength of M30. But in the case of soil, it doesn't have such a uniform behavior throughout the depth. No, that is called stratification. In this case, I'm just imagining there is a 2 meter depth of non-liquefied crust, and after that there is another layer which is very loose and liquefiable sand. Here again, that starts the non-liquefiable sand. So here, if any cyclic load happens, what will happen? My liquefiable soil started to get liquefied. Because of the liquefaction, the lateral movement, this will actually create a movement on this direction. But this non-liquefied sand, because of this lateral load, obviously the superstructures also started to move in this way. So because of this liquefaction, potential soil try to move in this way, but your non-liquefiable sand at the bottom will resist that movement. So your movement will be on the both the direction, which means opposite to each other. At this point, your pile started to buckling. This is called buckling failure. So this failure actually imposed into your superstructures also, right? So there are a lot of problems or effects or failure happens because of the liquefaction. I am just listing out few points here, right? So we have seen uplifting of the structures, tilting of foundation, lateral spreading, as well as buckling of piles, right? Now, evaluation of liquefaction potential. I think this is a very big topic. I don't want to take a whole topic or whole evaluation process of liquefaction potential. I'm just giving very glimpse of to that. Okay, so when to undertake liquefaction study and step-by-step procedure to evaluate liquefaction and the factors governing the liquefaction, right? So first, what are the factors governing the liquefaction? Magnitude of the earthquake, whether it is 8, 7.5, 6, 8, 8.5, or something like that. Right. A strong ground motions are needed to induce liquefaction. You know, if your magnitude is 5, I don't think there won't be a liquefaction. But it is more than 7.5. Yes, there is a high chance of liquefaction. Then, if the magnitude of the earthquake is low, it may not trigger any ground motions, right? Then, type of soil. Strata dictate the liquefaction potential of the sites. As I mentioned earlier, if I was in the person, definitely I would have asked this question to the audience. But now I cannot, ask audience. Let me ask the question and tell me let me tell the answer itself. No, what type of soil actually highly prone to liquefaction? Just think, you just think by yourself and come up with the answer. I will give you another 5 seconds, maybe 10 seconds, maybe. No need to tell. You just recollect the lecture that I have given so far. Okay, fine. Those who are actually say sand is the more prone to liquefaction, actually give applause to you, because sand is the type of soil which is prone to liquefaction to the most, not the clay type of soil, right? So obviously type of soil definitely will influence the liquefaction potential. Then percentage of fines content in the soil. Obviously, if your fine contents here, they are mentioning a soil passing through 75 micron sieve does not have an impact on liquefaction. So if your fine contents are more, like even if I'm having a sandy soil, but the silt or fines content are more, like 20 to 30%, that soil doesn't have a proper potential for the liquefaction. Then with the increase in the fines content, chance of soil to liquefy will reduce, obviously, because fine soil possesses some cohesive soil strength, shear strength, right? Correct. Then groundwater condition. Groundwater condition is actually plays a major role here. Depending on the saturation condition of the soil, liquefaction may or may not occur. In dry soil condition, where the water table is at a greater depth, liquefaction will not govern, right? So let me tell one more point onto that. To liquefaction to indicate, your soil needs to be a saturated one. If it is saturated one means, then your pore water pressure will build up. But just imagine, in your substructure or subsoil up to 10 meter or 15 meter, there is no groundwater. Maybe in a dry area, arid areas, there is no water table until 10 meter or 15 meter. Even there is a sandy soil, even there is a very loosely packed soil. If cyclic load attacks, now there is a no chance of liquefaction to be happen here, because there is no water present at the particular depth. So there won't be any pore pressure development. So groundwater condition is an important factor again to mm, assess the liquefaction. These are all the governing factors. Now, when to carry out the liquefaction study and how to carry out the liquefaction study. I am not giving the how to carry over. I'm just giving a when to carry out, right? So first, the high chance of liquefaction to happen is poorly graded, loose, saturated sands. Actually, I give three scenario here. First, it should be a poorly graded. Poorly graded means it's a uniform graded. People might know who have done the soil mechanics laboratory might know this poorly graded terminology, which means a particular soil particle is predominant in that particular soil mass. For example, I'm having a 1 kg of soil in hand. In the 1 kg of soil, almost 80 to 90% of soil particles in the same size, like 3 to 3.5 mm. If that is the case, that is called poorly graded. Why it is actually making poorly graded a liquefaction potential soil means, since it is a poorly graded, the interlocking between the particles will be very less. Okay, so since the interlocking is very less, there is a high chance of voids presence in there. If it is a well graded soil, there will the all the type of all the particle size will be present. So a smaller particles will actually occupy the gap created between the two successive bigger particles. right? So there won't be any voids. If there won't be any voids, then there won't be any water. If there won't be any water, there won't be any pore pressure dissipation. Sorry, pore pressure buildup. If there is a no pore pressure buildup, there is a no chance of liquefaction. Then loose sand. Loose sand means if it is a properly packed dense material, now obviously your voids will be less. There is a less chance of liquefaction. Then saturated sands, the soil should be saturated. The water should be there to get a liquefied. If there is a no water, there is no liquefaction. So these three conditions I am giving: poorly graded, loose, saturated sand. If these three conditions exist, then there is a high chance of liquefaction, right? Then obviously, most of the geotechnical investigation is being done with the SPT across India, because there are a lot of methods has been followed in the European countries and Western countries, but still India stick with the SPT values, started penetration test that is give the N values, right? So based on your N value, you can assume that the whether the soil can be liquefied or not. This is only assumption. I'm again telling this is only assumption, right? If your soil is N value is less than 10, this is actually falls under the seismic zone of 2, then there is a no chance of liquefaction, right? Then sorry, there is a chance of liquefaction. If your SPTN value is less than 15, but your area, your zone is coming under the seismic zone of 3, 4, and 5, then there is a high chance of liquefaction here, right? Then it does not clearly state that liquefaction analysis can be skipped if the above conditions are satisfied. Yes, this is the only hint to the designer. You should not stick exactly with these 3 points. If I'm soil is having a more than 10 SPT value, like let us take a 12 SPT value, but it is falls under the seismic zone of 2. That doesn't give 100% assurance that the soil will not liquefy. So you have to do the liquefaction analysis for that also, that I'm clearly mentioning here, right? Then, so as of now, I have given a glimpse of liquefaction, how it is happening, what are the possibilities of happening of liquefaction, what is the effect on your structure because of the liquefaction I have given. Now, I hope you understand some point. Probably this is just an introduction. If you want to know more about liquefaction, definitely you have to go through the textbooks and the references books, right? Now, because of now coming back to the erosion and scour, as I mentioned, we have clearly taken 4 points, 4 impacts on your geotechnical aspects because of the cyclic loading or a cyclone prone area. So we have taken uplift of your foundation. We have seen that liquefaction. We elaborately seen that. Now we are coming back to the erosion and scour. So what is erosion? What is scour? Let us see. So erosion. Right. So erosion is again classified into 2 parts. One is water-induced erosion, another is wind-induced erosion. So first, water-induced erosion. This is happening because of the rainfall and the rivers and ocean waves. These, just imagine rainfall. In the case of cyclone, the rainfall will be very heavy. In the time of cyclone, the river movement will be very high, right? And even because of the heavy rainfall, your flow of river water will be very high, and it get wider and wider, right? So then the same case to the ocean waves, that is because of the storm surges. So storm surges, river movement and heavy rainfall will make your, this is the example picture I have given. This is the erosion. But initially your sea line will be here or shore will be here. Because of this cyclone, that is a storm surges will actually make your sea water to come until this point. It gives the erosion. This is a rocky strata get eroded by the sea water. Just imagine if it is a structure over here, right? So this is the water induced erosion. Then wind induced erosion. This is because of strong wind dry areas. There is no water or rainfall play role here. Only wind, heavy wind. It is no heavy wind occurring in a dry area. Just imagine this is a dry area. Just imagine as a desert. Yeah, fine. It is a dry area. Yeah, a very high wind profile is coming. First, what will happen? The deflation is happening. Deflation is lose the soil particles. If it is already dry in a density condition, make it loose. So deflation happens. Now the soil particles become individual particles. Then abrasion. So these particles will actually move. The transportation of this deflated soil particles can be transported into three ways. One is suspension. The finer particles get into the wind and actually mix it with the air. So like if it is a silt and clay particles, obviously it have a fine particles. It will actually thrown by the air and mix it with the air. It's just called suspension. If it is a coarse grain material, it cannot float. So this will happen of saltation. So this is actually moving from one place to one place, and this is a creep. Creep means a slow movement. If it is a huge particles, it will go slow by slow. So at one point it's getting deposited. So the area of soils get transported by the heavy wind and deposited in another area. It is called wind induced erosion, right? So because of this deposition, dune formation is also happening. That is called sand accumulation in the particular area. Actually in the LNT we are actually facing a lot of problem because of this dune formation during the construction in the Gulf countries. We are actually working, doing some research on how to construct on the dune formation and how to rectify kind of dune formation, right? Now scour. Scour is is nothing but erosion, but it actually removal of particular sediment around a particular structure. You just put it in that way. If you have a pile foundation or if you have a shallow foundation, definitely you might have backfill that material around your foundation to give the lateral support to your structure, right? Because of the heavy rainfall or movement of water, the surrounding soils has been removed, that is called scour. Now what happened? Your structure is losing your lateral strength. So because of losing your lateral strength as well as the axial strength, your structure will get failed. So that is the effect of scour here. So scour is the removal of sediment from surfaces due to the force of moving water. So it commonly occurs in rivers, streams, coastal areas and around structures like bridges and seawalls. Here the example picture I have given, this is a actually a bridge from here to here. Because of the scour, the foundation got failed, then the bridge got failed here. So this is the effect of scour, devastating effect. Scours can be typed into five again. Local scour to happen around the obstacles like bridge piers where fast moving water removes sediment. So this is a perfect example for the local scour. Then general scour. So affect entire riverbeds or coastline due to the natural water flow. So this is the example here I have put. So and this example can be taken for both erosion as well as general scour. And contraction scour, where your heavy speed water from the any streams like river or any other running water streams, it actually moving through a narrow section. What will happen? So it will actually take all the material around in your surrounding structure. So that kind is called contraction scour. Then wave induced scour, because of the ocean waves and tides leading to the coastal erosion. And tidal scour, because of the tides, it actually takes a lot of shore scouring everything. So if you take, let us put it in the simple word. If you take a surrounding soil out of your any existing structure, it loses its supporting, lateral resistance. Your structure is going to fail. So in a simple word, a scour will remove the sediments around your structures or any foundations, that will automatically make it fail. Simple. Then effects on foundation by scour. Since it is a geotechnical consideration, I should talk about foundation, not about the superstructure, right? So first, loss of support, loss of lateral and vertical support of the foundation leading to instability. Then settlement. And the foundation may settle unevenly as the soil beneath it's eroded, right? So once the soil beneath the foundation is getting removed by the scour, obviously the foundation gets settled. Once the foundation gets settled, building gets failed. Then reduced bearing capacity. The foundation's ability to carry loads decreases as the foundation is removed, right? Then structural failure. Severe scour can lead to tilting, cracking, or collapse of the structures. These are all the effects on foundation by score. This score actually given by the cyclone, right? That how the soil properties influence the structural stability. As of now, we have seen what are all the dam and consideration should be given for the cycling prone area. What are the damages actually it will create? So we have seen in detail what are the damages like liquefaction, erosion, and scour. Now how the soil properties influence the structural stability, right? So soil properties such as shear strength, compressibility, and permeability determines the foundation ability to support the loads and resist deformation. So these three properties called shear strength, compressibility, and permeability is known as engineering properties. Soil properties can be divided into two. One is index properties, another one is engineering properties. Engineering properties is nothing but the property which affects the structure above your soil is called engineering property. Let me put in a simple term. Shear strength obviously governed by the angle of internal friction and cohesion. The soil has its maximum shear strength. Once it is loses shear strength, building fails, right? So shear strength needs to be more to keep your structure intact. So it is a direct correlation, direct proportion. Shear strength is more, your structural stability is more. Next, compressibility. Compressibility is ability of your soil to compress. If you are able to compress your soil more, means your soil is in the loose condition. Your soil is in a very soft nature. So your soil should not be more soft or more lesser dense. So it should not compress more. So it is an indirect proportion to your structural stability. If your compressibility is more, structural stability is very less. The same goes to the permeability. If your soil is more permeable, which means it allows the water into the soil. Once the water enter into the soil, obviously soil gets failed. So this also makes an indirect proportional. If your permeability is more, stability is less. Permeability less, stability is more. So these are all the important soil property to be considered for your structural stability before anything to be constructed over the soil. Okay, so please keep this in mind. No structural stability. If you talk about the structural stability, without knowing the soil properties, you cannot design everything, anything at least. Then poor soil condition. It is a loose and expansive soils can lead to settlement, tilting, or failure of the structure under cyclic or even static loads. Not necessary to be a cyclic load. Even a static loads give this kind of failure if your soil is in the loose condition. Expansive soil is another big topic you cannot take now. Just imagine it is a black cotton soil. In colloquial terminology, we used to say it is a black cotton soil. But in geotechnical terminology, it is called expansive soil, which is having a high swelling and shrinkage nature. If your soil is having, a lot of water holding capacity, if water, heavy rainfall comes, your soil started to swell. If soil under the ground it swells more, what will happen? The structure above the soil is gets heaved. It's get a crack in your structure. In the same soil, in the summer time or in a arid area, what will happen? All the moisture content will be removed. Your expansive soil has a shrinkage. It started to shrinkage, which means a reduction in the volume. Obviously, this will actually keep your structure to settle. So these are all the problem related to this loose and expansive soil. So structural people, please keep in mind that if you want to construct or design a proper stable structure, you have to consider these properties of the soils first, right? Then importance of the soil investigation and testing. This part most of the site people are not actually doing properly, because site investigation is a very, very important thing to design anything, like not only the foundation, even for the superstructure, right? So the soil investigation provide critical data on soil type, strength, behavior, enabling engineers to design a safe and stable foundations. So now, there are a lot of soil investigation methods are present. Starts from the direct method, indirect method, and semi-direct method. Direct method is like making a test pit and seeing the stratification of the soil and take the sample to the testing. But that is actually limited to the particular depth. You cannot go beyond 3 meters for the open pit testing, because it takes a lot of human energy to go beyond 3 meters in the open condition. Then indirect method, obviously there is a borehole method that is called SPT, standard penetration test. You can take the soil sample, below 100 meter, 200 meter. Even in the Gulf countries, the project called NEOM is happening in in Saudi Arabia. There the borehole has been taken from 200 meters from the surface. People are taking sample from the 200 meters from the surface and doing the test to know about the soil properties below 200 meter to 300-meter depth. Just imagine how depth they are, how deep they are going, right? And another semi-direct method is called CPT, called cone penetration test, that will give you the soils properties. And indirect method, geophysical method, and that is called the seismic refraction, electrical resistivity method, GPR, and there are a lot more of cross hole seismic testing method is also there. So at this time, I regret that I cannot explain more about the testing facilities on the soil investigation. But keep it in mind that investigation also plays a major role in determining the soil types and strength. So if you fail to indicate what type of soil it is by doing a bad investigation, that will actually affect your structure during this kind of challenging situations like cyclone or any kind of earthquake, right? So testing helps identify the potential risk like liquefaction or settlement, ensuring appropriate mitigation measures and implemented, right? Then coming to the foundation design of cyclone resisting structures. So I think we are running out of time, ma'am. We have time, ma'am. Hello, ma'am.
Sir,
Hello, ma'am. Do we have time, ma'am? We have another how many minutes, ma'am? Yeah, fine. I hope I will take another 10 minutes to finish it off.
yes, sir,
Right?
yes, sir. Please take your own time, sir. No issue, sir. Next session
Yeah,
will
fine.
start on 8 o'clock only, sir. Please take on,
Okay,
sir.
okay, fine,
Okay,
fine.
thank you, sir.
So this is the foundation design for cycling resisting structures. So as you all know, foundation types can be bifurcated into shallow foundation and deep foundation. Though the shallow foundation, again, it can be called as a spread foundation, mat foundation. Mat is nothing but a raft. This spread foundation can be divided into, again, square foundation, I mean, rectangle foundations. There are a lot of, so just keep it in the simple term. It is a spread foundation, and there is a mat foundation types also. In the case of deep foundation, it is a pile foundation, drilled shaft that is called caissons and piers. These are all deep foundation types. So let us not go deeper on the types of foundation now. Just keep it in mind that your length by width to depth ratio is more than 5. That is called the deep foundation here. In that level, you can keep it in your mind. Now, to design that such a foundation, what are the loads we are considering, right? In the shallow foundation, dead load and live load. Obviously, since you are structural people, definitely you might have known the dead load and live load, and wind load. You might have considered that, and seismic load. Definitely you would have considered that. But in the probably you might not design the deep foundation. So for designing the deep foundation, we have to consider a lot of loads: axial load, lateral load, uplift force, and cyclic loads, and scour and erosion. So here, this scour and erosion you have to consider, cyclic load you have to consider, uplift force, lateral. These three part actually cyclone will impose here. So wind and seismic activity will give a yes. So wind and seismic activity actually will give a lateral load here, and wind and buoyancy effect will give the uplift forces here, and repeated loads from the waves actually give the cyclic load to your deep foundation. So if you want to design a proper deep foundation, so you have to consider all these loads, especially these three loads in the cyclic prone areas, right? Right. Now, so at what point or what structures we have to consider the wind load. So the wind load must be considered in the following situation. Tall structures, buildings or towers with the height to width ratio greater than 4, that is categorized as the tall structures. To design the tall structure, you have to consider the wind load. Then exposed location. Here you have to see in the open area, there is a no structure at all, but you are constructing a high-raised building like 20 story or 30-story building. In kind of open area, the wind force will be directly hit on your structure. But in the case you are actually, your structure is actually one among the 20 to 30 structures, the wind load will be shared by the mini structure. So the effect will be divided into 1:20. The same goes to the coastal regions and hilltops where the wind speeds are higher. So these are all the locations. Exposed locations are, you have to consider the wind load. Then lightweight structures, buildings with lightweight material, steel frames or glass facades that are more susceptible to wind forces, that you all know that. Then cyclone prone areas, regions with the frequent cyclones or hurricanes where the wind speed can exceed 120 km per hour. So in this area, you have to consider the wind load for your design. Then flexible structure, structural with a low natural frequency, long span bridges, transmission towers that can resonate with the wind forces. If you are following my presentation from the beginning, you might have heard the natural frequency of the structure in the initial slides. So if your natural frequency of your structure is very low, means definitely it can resonate with the wind force. If both the frequency are resonates, definitely the impact will be more, the failure will be more. So the flexible structures which is having a low frequency, if you are constructing that, then you have to consider the wind load also. So that is the wind load part. Now coming to the pile design. In the geotechnical part, we are actually not designing any structural part of the foundation or structural part of the pile, which means we are not actually calculating how many area of reinforcement we have to give, what is the number of reinforcement we have to give, what should be the spacing. Those things in the geotechnical area, we don't actually consider that. Here, the foundation design mainly give the capacity, bearing capacity, load capacity of the particular pile, right? So mostly this 2911 IS 2911 actually gives uh, two categories, two loads, axial load as well as the lateral load capacity. Here, axial load I don't want to discuss because that is a very common, and cyclone resisting structure we don't obviously we consider the axial load, but in the case of cyclone resisting structure, the lateral capacity of the pile must be considered. So that is why I have put only the lateral capacity of the pile. So if the lateral load is considered for the pile foundation, the equivalent cantilever approach gives a simple procedure for obtaining the deflection and moments due to the relatively small lateral loads. Here you can see here, this is two types of piles. We used to say that, free headed piles and fixed headed piles. Here it is called fixed head pile. Here it is have a free headed piles. Free headed pile means your pile is actually prolonged above your surface, which means there is a considerable amount of length is actually open to the air. The Q is lateral load. If you if you consider the lateral load of Q, in terms of lateral load in kilonewton, there is a formula to determine the deflection. Here, the deflection as per the 2911, the limit, the lateral displacement limited or acceptable lateral displacement, you can call it in that way. The acceptable limit of lateral deflection of the pile is actually 5 mm only. Okay, you cannot go beyond that. So if you put a y as a 5 mm, this all the parameters are known values. E is the Young's modulus, I is the moment of inertia, and ZF is the depth of fixity, and D is the distance between the surface and the tip of the pile. So this call everything is a known value. The H can be calculated here. For example, I am putting 5 mm here. I am putting every parameters here. The what answer I will get, that is the H. That is called lateral load in the kilonewton. So for that, for my particular pile, can withstand this much of lateral load for achieving or to withstand until 5 mm. So for example, it is giving a 110 kilonewton of lateral load for a 5 mm means if you're expecting a wind load of more than lateral load more than 200 means your pile is actually not satisfying. Now you have to change the pile dimension. So that is how you have to make, um, with the 5 mm constant, you put all the parameters based on your assumed pile dimensions, you will get the lateral load. If your lateral load that you are expecting on a particular site, if it is both are matching, then you can actually say it is a safe design. But you are expecting H more than the coming value, then your pile is not satisfying the requirement, then you have to go for a higher piles. Higher pile means mostly 2 piles or 3 pile groups, or else you can go for a higher diameter piles and higher length of the piles. So that is the way. The same way we can calculate the moment also, fixed end moment. You can calculate by deflection or calculate by moment. Both are similar conditions, but what you have to do is you have to find what lateral load my designed pile can withstand for a 5 mm of deflection. That's all. So you have to see this H is equivalent to the expected wind load from the expected cyclone on a particular location. Simple. So that is for your lateral load. Now uplift capacity. How we can actually calculate the uplift capacity means, again, this is not, just not not like your lateral displacement or lateral capacity. Uplift capacity cannot be calculated using any analytical method. It is a simple site investigation. Site test. So you have to make one test pile with a reinforcement at the cutoff. This is called cutoff level, where you actually make your reinforcement to visible. Here the reinforcement can be used for your pile cap and the upcoming foundations. So this cutoff level, you have to connect another reinforcement layer to keep it here. This is your loading frame. This is your hydraulic jack. Just imagine this is connected to your pile foundation reinforcement. If the hydraulic jacks moves upwards, this reinforcement connected to the pile will try to, take uplift your foundations. So how much resistance is given by your pile foundation against your uplifting force is called uplift force. Hope you follow this point, right? I am not giving any tough terminology at all. It is a very simple. Here you keep your dial cages here. This is your cutoff level. Since you are applying your hydraulic load here through the reaction frame, the connected reinforcement to your pile reinforcement will try to make a uplift. So this uplift actually give the movement of your pile in the dial cages. So here also uplift movement also the what is it called? Allowable uplift movement they have given is a 12 mm as similar to the axial displacement. So you have to find whether my designed pile or the designed uplift force giving 12 mm displacement or not. If your pile is giving only 10 mm, 10 mm of uplift displacement against your given load, then your pile is safe. If it is more than 12 mm, your pile is failed. You have to go for a better pile, which means you have to improve the diameter and the length. By increasing the length, you may expect a more resistance from your frictional resistance. That is a different part, pile calculation. Fine. So this is filing criteria. I put it in the words here. This is how your lateral capacity of the pile can be calculated. Right here is your test pile. Here the hydraulic jack is happening. Applying the load on the lateral direction instead of the upward direction. Here this is the datum bar to note down the displacement of the pile. Just imagine I am applying the jack here. The pile is started to move. The movement is actually calculated or fined by the dial gauge here. If your movement is less than 5 mm, then your pile is safe. It is more than 5 mm, your pile is failed. That's all. So the loading should be applied in the increments of 20% of the estimated safe local capacity. And the next increment should be applied after the rate. These are all, you can find it in the code. This is the how to apply the load for the lateral load test. Now, the point you should actually keep it in mind is 5 mm is the allowable lateral movement for any pile foundation. That point is enough for you to understand. And here, what are the failing criteria for the pull-out test? For piles up to and including 600 mm diameter, 2/3 of the load at which the load displacement is 12 mm or the load correspond to the specified permissible uplift. Sometimes a particular site may give a specified permissible uplift limit other than 12 mm. So you can actually calculate that also, or else you have to take your piles safe uplift load is 2/3 of the load, which makes your pile to displace 12 mm. That is the load settlement curve. You can get it from the load settlement curve. That is for your less than or equal to 600 mm diameter. If your pile diameter is more than 600 mm diameter, then the allowable uplift can be given into 18 mm. And there are other criteria to be noted down here. These are all like, you can find it in the IS code 2911 part 1 and section 2. So that can easily you can take it out. And as of now, we have discussed what are the effect of cyclone on the geotechnical aspect as well as structural aspect, and what are the tests to be done, what are the foundations to be designed on what aspects, what are the important specifications or aspects to be considered for design of foundation to mitigate the cyclone thing. Now, okay, everything is considered. Foundation has been done. Or foundation to be, my area is cyclone prone area. Now I am going to construct a structure on that, but my soil is not that much good. I cannot improve the soil. That is ground improvement is there. Now let us see, not going for the ground improvement. in the foundation level, what are the mitigation level I can take up? How to overcome these issues. Use a better materials and quality of concrete, corrosion resistant material in coastal areas, and anchoring and bracing of foundation. Here you can see the under-reamed pile here. The pile which is having an under-ream, this is called ream pile. So you should have under-reamed pile. So this under-ream pile actually withstand your uplift pressure. If your wind load is happening this way, then what will happen? This pile definitely will go compression. This pile will go uplift. This uplift movement will be resisted by the under reams. This is one way of mitigating thing. And this is anchoring. This is our shallow foundation. Here I am providing a shallow foundation, but this shallow foundation is provided with the anchor here. This is a steel anchor with a rounded plate here. Above this rounded plate, I am actually provided GAP material. 10 more minutes. So this is GAB material. So this is GAP is nothing but a grouted material. So this can be grouted around your anchor. This anchor will be actually withstand your foundation against of your lateral movement or any uplift portion, right? So this is same goes for your bracing. Here the retaining wall structure is that there is a what is it called? Retaining. This is the retaining wall. This is your retained material. So if your material is actually moving this way, your retaining wall gets to fail. So this can be braced like this. So any lateral movement can be arrested by this bracing. So this way, here I provided just only examples. In a lot of way, you can actually prevent these kind of issues offered by or imposed by the cyclones. So how important the investigation? I already mentioned how important the investigations are. So you have to do a proper investigation to know the soil properties. Without knowing soil properties, you cannot predict your soil strength and how good it will be withstand against your cyclone. So you have to do the field test, SPT, CPT, and plate load test and laboratory test to find out the engineering properties and the basic things. So how advanced are the analysis? Now, obviously, there are a lot of softwares has come across. For example, Plaxis and GeoStudios and many more software has been come. So using this kind of softwares, you can actually design any slope stability, bearing capacity failures, and settlement analysis. In beforehand, you can do all the analysis with the input parameters. So you can easily do the analysis whether my design of pile is good enough or whether the slope stability is good or bearing capacity is good with the get input from your site investigation. So everything is depends on your investigation. If you do a wrong investigation, you will get a wrong input parameter. If you get the wrong input parameter, you will put upload the long input parameter here, you will get a misleading analysis. So even though it has been analysis has been improved a lot, everything depends on the investigation again. So you have to do the investigation properly here. Then mitigation of the mitigation strategies of the and best practices. I know liquefaction is there. There is a lot of soil problems will be imposed on by the cyclone. So how I can mitigate? The basic thing is soil improvement technique. You have to improve the soil, like making a compaction better, grouting using cement or any other chemical products. There are a lot of chemical products available for the grouting and the soil stabilization. Soil stabilization means anchoring is there, bracing is there, geosynthetics there. You have to all those things actually indicates that improving your soil's compaction, which automatically improves your bearing capacity. Then use of geosynthetics and reinforced earth. This is another huge topic that I hope I can take to you people in future collaborations, right? So this is a soil improvement technique which actually mitigate your liquefaction or cyclic prone problems. Then early warning systems. The role of meteorological data in cyclone preparedness. You have to keep your early warning system, which means the cyclone going to happen. That early warning make you ready for your structural stability in many ways. An integration of early warning system in the design which keep your structural stability intact. Then community and regulatory involvement. The importance of building codes and standards. You have to stick with your building code standards. You have to stick with that. If you give a compromise on that, definitely you have to compromise on your structural stability also. That will lead to the huge fatal accidents. I think that's all from my side. Thank you, ma'am.
sir. Thank you for your wonderful presentation, sir. Thank you.
Thank you, ma'am. Thank you. Thank
Participants, any question and answer? Faculty members, kindly ask your doubt.
Yeah, please. So if you have any queries, just please ask.
Sir, attendance feedback and session feedback will share in the end of the session, sir.
Okay, ma'am. Okay, okay.
Okay, sir. Okay, sir.
So, shall I stop the sharing, ma'am? Hello? If no more questions, shall I stop the sharing? Okay. It's a wonderful opportunity. Thanks for the college SSN and civil department. I'm very happy to present the topic called, geotechnical consideration for the cyclic prone area or cyclic resistant structures. And happy to, meet such a huge numbers, 134 people at the time of 740 is not a joke, If you are not actually really interesting, you cannot be here. Thank you all. Thank you all. I hope meet you all in another collaboration. Thank you.
Sir, excuse me, sir. There is a question, sir.
Yes, please.
Sir, it is in chat box, sir, by Saravanakumar, sir.
Yes, please.
Sir, is quicksand condition possible during cyclone?
Yeah, quicksand condition is a byproduct of liquefaction. Quicksand condition is not a separate phenomena. It is a byproduct of your liquefaction. If liquefaction happens, obviously quicksand condition also happens. Yes.
Okay, sir. Thank you, sir. Thank you.
Any other
Thank you,
question?
sir. Thank you, sir, your valuable presentation. I
Thank you,
hope
thank you, thank you.
the participants will enjoy the session and get knowledge. They asking our PPT, sir, will share at the end of the session, sir.
Yeah, sure, ma'am. Actually, I will send it to you in the mail. You can share it to the people. Thank you.
Yes,
Yeah.
yes, sir. Thank you once
Thank you so
again.
much. Thank you. Thank you.
Please,
Thank
sir,
you,
please,
everyone.
sir. Thank you, sir. Thank you, sir. Ram Kumar.
Yes, ma'am.
Please join the session, Ram Kumar. I will start our next section.
Okay, ma'am. I'm just ready. So
2 minutes. 2 minutes. 2 minutes.
okay, ma'am. Sure.
So good evening, professors. And I hope your first session will be useful and you are enjoying the session. Now we'll continue the next session. The session will be presented Engineer Ramkumar Bharati, Civil Marine Project Engineer, Macron Dowell, New Zealand, Australia, Pacific Iceland. Hello everyone. Now for the second, it's my pleasure to introduce our resource person for today's session, Mr. Ram Kumar, Megan Donald, New Zealand. We sincerely thank him for joining us and sharing his valuable time and expertise. SARS has highly skilled marine civil engineering with over 11 years of experience in civil and marine construction projects across New Zealand, Australia, and the Pacific Iceland. He has been part of a wide range of projects, including bridges, highways, dry docks, jetties, breakwaters, dredging works, and land reclamation project. His expertise and extend to advanced construction techniques like installing temporary cofferdam, sheet piling, diaphragm wall, and various marine structural works such as repairing and strengthening marine structures. Academically, he holds a bachelor degree in civil engineering from Anna University and a master degree in construction engineering, graduating with distinction. He also had additional qualification in quantity surveying and an MBA in project management. Currently, he is contributing his expertise as a marine and civil project engineer for McConnell Dowell, New Zealand, where he leads key infrastructure projects, including the construction and upgrading the water sector for Australian Defence Force and various development works in the Solomon Islands. We are privileged to have him with us today to share his insights and experience in marine and construction. Let's give him warm welcome. Welcome to our session, Ram Kumar. And one more information, he is my UG student. I'm very proud of him. Thank you, Ram Kumar. Please continue your session. Now time is yours.
Thank you so much for your valuable introduction. Good evening, ma'am, then SSM College Institute professors and the management team, students and ladies and gentlemen who are joining this session. Thank you so much for giving this valuable time and the day. It was good by Mrs. Selva Bharati ma'am, and it was valuable. It was so valuable to me to presenting my valuable experience, which I was gained from the New Zealand and Pacific Islands and Australia. So the topic is very critical, but there is a huge information available with me. So I'll be ready to share with you. Thank you so much, ma'am. So shall I start the presentation? Selva ma'am. So shall I start the presentation?
Yes, sir. Yes, sir.
Yep. So I'll just share the screen. So I think everyone, this is my screen.
Yes, sir.
So I start the presentation. I have very less time.
Yes, sir. Yes, it's visible only, Ram Kumar. Please continue the session.
Yes. The topic is the resilient infrastructure for the cyclone-prone areas, and this is mainly for lessons learned from the Pacific Islands, which is the theme is the engineering solution for the climate adaptation. So this time presenting myself, I'm the Ram Kumar Bharati, project engineer from McConnell Dowell Constructors, Australia Private Limited. I'm working in New Zealand. Mainly, I'm working in the project of the Australian Defence Force, the wharf construction, which also related to the resilient infrastructure project, which was funded by the Australian Gate and the government of New Zealand. So I'm going to start the first slide. So the first of all, the cyclone-prone areas. The cyclone-prone areas, which is the regions frequently exposed to tropical cyclones, which was characterized by the strong winds. That is a category 5, 4, 3, 2, 1 in the Pacific Islands and as well as in New Zealand, Australia, with a heavy rainfall and storm surges that cause significant damages. You can see that most of in the world, the Pacific Ocean is the most dangerous ocean, as well as this tropical climate. Suddenly, the climate may change at any time, at any weather. There is no specific weather condition. There is no specific climatic condition because of due to the climate change and pollution. We are experienced that much of severe cyclonic storms, which was experienced in so many Pacific islands, and namely in the Solomon Islands, Vanuatu, Fiji Islands, American Samoa, even this was experienced by New Zealand. Even Australia also in the past 1 week before the Pilbara port was severely affected by the cyclone. So this geographic focus is the mainly like what I'm saying, that Fiji, Vanuatu, Tonga, and the Solomon Islands, these are very severely affecting each and every year. So the World Health Organization, as well as the Australian Health Ministry, they are categorized, these are all severely affecting. The fatality was increasing due to the cyclone prone areas. So particularly these are all completely remote locations. These are all not developed. This is the developing nations. These are all funding by the Australian government and the New Zealand government. So the main impact of the cyclone is the loss of lives. The thousands of fatalities recorded annually in the cyclone-prone regions. Even the last year in Fiji, it was around 550 fatalities was happened due to the cyclone. The property damage, a extensive destruction of homes, schools, hospitals, infrastructures, airports, and as well as connectivity to one island to another island. So this is compared to India, these are all cyclone periods very severely affecting each and every year. Mainly, the cyclone-prone areas are mainly affecting by the economic impacts. The first thing is the fatalities, the health issues. Then second thing is economic impacts. The disruption of tourism and agriculture industries and the long-term recovery cause strain national economics. This economic is the main thing is the decreasing of currency value and the inflation, then the export imports, everything it was the main problem which was occurring in the particularly this Pacific islands. So the resilient infrastructure importance is the theme is to minimize damage and enhance the recovery of the country, then protects lives and livelihoods, then supports the sustainable development and economic systems in the vulnerable regions. So this is the main thing. What are the project, the consultant proposing the feasibility studies, these are all key factors that may consider for the projects, where what are the countries this mainly affecting by that, mainly for cyclone and even sometimes earthquake. These are the key things which will be considered for the feasibility studies to developing such nations. This you can you everyone as aware about the port warning signals. Once a cyclone is developing, that already this with the just images, the satellite constellations, the meteorological department will arrange some data for the crossing and cyclone impact, then dangerous. Then that visual storm warning signals will be on signage permanently hoisted at the marks of the ports to alert ships of the weather conditions in the ports they approach. Because even I'm just particularly working in the port and harbor. So when the cyclone is, when the storm warning, when it is, we are getting information from the meteorological department on or else defense meteorology surveys, will be immediately just shut down the harbor because of the most of the Pacific Islands is very small. So you can search in the Google Earth, you can see in some very in compared to just except Australia, the rest of the New Zealand or any like Pacific Islands, these are very tiny, like you can see in the Google Earth. Because of even this area, this cyclone may cross very easily. So because of that line will be crossed over that sea conditions. So while the certain countries hoist the flags, for example, in my past experience when I was in there will be flags will be there. So the flags will be that's in most of the Pacific Island, there is no lighthouse. So in this case, what they will be built, they'll be just with the highmost tower. In the tower, they'll be just fix the hoist flags. So in the hoist, there may be signs. Sometimes they work. Sometimes the radio signals range will be maybe disconnect because of due to the conditions, because of this is developing nation, it's not completely developed. So in these cases, they will be hoist the flag, then we just give the warning signal the port may be in severe dangerous condition. So they may be just divert the ways to the ships or vessels to the center of the ocean where there is no damage from the cyclones. The day signals are combination of cylinders, cones. In the night signals are in red or white lamps. It may be not in solar, but that means some DC generator will be there. So you can see this image, a cyclone warning, which was we are following in the New Zealand or Australian Pacific Islands. These signboards will be fixed in the harbor entrance. So the people can may know, then the port employees can may know very easily that whether it will be no immediate danger or prepare for the cyclone or cyclone imminent, harbor closed. If the cyclone is a category 1 or category 2, will be immediately shut down the port. That means the port is going to be is in dangerous condition, even infrastructure as well as ships. So in infrastructure wise, we are already experienced. I don't have enough photos because that is completely in a different site. There is some restrictions will be there. There is no, we cannot able to, there is no permit to take some photographs. That what happened, this fenders and as well this pile and the structural beams, which was, that country was experienced very severe cyclone storm, which is around 230 kilometers per hour. So even the structures was constructed in 1995 in the year, so it was very severely damaged. Even the pile, the record pile, what we are installed in the 1995 in our Meconodol, it was around, the angle was slightly changed. That is 1:3, but it is 1:4.5. So these are all problems that we are experiencing and encountering in the islands, particularly the Solomon Islands or as well as in Fiji, in the New Zealand. So that you are seeing the signal flag or number, this usually in following in the southern countries as well as in India, Southeast Asia, in India, in Australia, New Zealand, and as well as in the Pacific Islands. So the signals that you are seeing, right? This is signal 1, 2, 3, 4. That is totally 11 signals are there. So signal 1 and 2 is already some low pressure depression at the sea, but port is not affected. So somewhere the depression was formed, but later the developing of the depressions. So later that we came to know about the cyclone, where it's the movement of the cyclone, where it is going to be crossed, which area is going to be affected. That everything will be common later period. So once a depression was formed in the sea, that will be immediately came to, we can raise the flag, or there will be rings will be there, or cone shape. So we'll be raised immediately in the port, because in the Pacific Islands, not like India, in India having the many major ports and minor ports, but in islands, there is only one port will be there. Each in the New Zealand, Australia, there may be the many ports, but in islands, that only one port will be there. So they may be raised the flag, or they may be raised the cones. So for this is a signage that people can came to know, and as well the sailing team can came to know that some depression was formed in the sea. So once signal was changed to 3 and 4, that bad weather. That bad weather means there will be the very heavy rainfall, that means the wind will be there. These signals will be categorized due to the wind speed of the cyclones. So the signal 5, 6, 7 is likely, the cyclone is likely to cross the coast. That means the signal is, this cyclone is going to be crossed in the islands, or near to the port, but not exactly at the port. Once a signal, it was raised 8 or 9, this means it's a great danger. The severe cyclone to cross the coast, left or its right. But the signal 11 is very severe. That I will share some past cyclones which was crossed up to signal 11. So once the signal 10 is raised, so it was fixed, then flag will be just keep fixed on the high mast. So immediately the port will be shut down. That means the country is going to be in severe danger of the cyclones. So all the alert teams and the local evacuation teams will be adopted, and other countries' aids will be present over there. The defense as well as local police will be adopted to evacuate the people from the coastal areas. So or else in some islands like Vanuatu will be there. So people will be completely evacuated from the country because it's very small islands. So signal 11, mostly in my experience, I'm not here any signal 11. Why? Because the signal, most often signal 9 and 10, the meteorology department will be declare that the country will be in severe dangerous condition. So mostly all the preparations will be implemented, then the evacuations will be started over the time. So the challenges in the cyclone prone regions. This, for example, what I'm going to share, that the Pacific Islands is completely remote geography area. Each and every island is completely, there is no link between the developed and developing countries. It's completely remote. So that they limit their resources and funding. Most of the countries now, wherever the Pacific Islands will be there, they are funding for the cyclone prone regions because there are already feasibility studies done. But even in this, but funding is very less. That is very limited resources to because there is no access to this Pacific Islands. But that's a lot of resources out there, which is local resources as well as this local fundings, the teams, and there is no proper the fundings will be not available in the particular islands because some countries need to be aid to give the resources to develop that. So the vulnerable ecosystems, for example, in some areas there is no access, even the cyclone prone regions. If one cyclone is affected, we cannot able to access to a particular region because of this. Sometimes the airport will be completely damaged. Then there is no access. Some trees may fall, then electrical poles may fall. Then sometimes the port and harbor structures may be affected due to the cyclone. Sometimes the damage may be severe. There is no berthing area for the vessels. Then highways may be damaged. The many things are there. So then in economic wise, the depend on tourism and agriculture may severely affect because most of the Pacific Islands countries are depending on the agricultures and tourism because there is no revenue for that country. So it will be severely impact for the economic. These are all the key challenges what the countries are facing due to the cyclone prone regions. The resilient infrastructure, the main thing, the resilient infrastructure is the infrastructure designed to withstand and recover quickly from the extreme events. This not 100% we cannot able to recover quickly because of due to the access. Because most of the not almost 100% of the highlands in the Pacific region, there is no proper access. Still, it is developing. You can hear the around 1 month before there was very severe earthquake was happened in Vanuatu island. The very next week, there is a cyclone was crossed over that Vanuatu. So in these cases, even the country is experiencing very severe infrastructure damage as well as the access. So that engineers that we need to be consider the components of the structural and operational and community resilience, particularly that when we are preparing the feasibility studies, the resilient infrastructure, that engineers or consulting engineers that we need to be consider those infrastructure opportunities. So the principle of resilient infrastructure is robustness and redundancy and resourcefulness and recovery. So mainly the ability to withstand the extreme winds and flooding and storm surges without significant damage. For example, if we are constructing any structures, reinforced concrete structures, that should be in elevated foundation. Most of the things is in elevated foundations. Sometime what happened, the port and harbor structures after the cyclone, there may be the severe erosion will be there. So next, the redundancy is incorporating multiple layers of protections to ensure continued functionality during the disruptions. Example, backup power system, alternate evacuation routes. What happened, for example, the thing happened in Japan. Japan, what happened due to one cyclone? I forgot the name. The cyclone was affected severely the particular region, Okahu. In that particular Okahu region, there is no power backup, but there is a nuclear power plant was there. After that, due to the complete power shutdown, the plant is unable to cool. So what happened? The radiation was emitted over that area. So these are all things, the resilient infrastructure, the redundancy examples. So the engineers or consulting engineers that need to be considered the factors when they are designing the structures. Then resourcefulness, the efficient use of available resources, particularly local resources, and quick adaptation during emergencies. Example, the modular construction techniques and local sourced materials. Usually the island which is located in the Pacific or in Atlantic region, there is no proper easy access because of if you are ordering any materials, it will not available very easily because we are just most of the islands are depending on developed nations like Australia and New Zealand. So in these cases, we need to develop the local material and local construction techniques using the local construction materials. Most of the PhD projects are on like developing the construction materials, which are the materials available locally, like it environmental friendly. So the recovery is mainly the quick restoration of the services and infrastructure after a cyclone. Example like pre-established recovery plans and residence supply chains. In this recovery case, most of the Pacific Islands is not a very quick recovery because of main thing is the resources and the aid. The aid will not available very quickly because of the country need to send the separate team to recovery, but it will take maybe the 90 days, maybe 90 to 120 days to analyze the recovery. So you can see like in developing nations, the India's compared to means the Pacific Islands, India is very good in the recovery of the team because of that is a lot of examples for easy recovery, but in the Pacific Islands it's not that much easy because of it will take 90 to 120 days because of the main thing is access. There is no access. This is a practical because we can still theoretically we can recover within a month or within a year, but still there is 2015 that one cyclone was affected in the Vanuatu and Fiji. Still it was not recovered properly because of there is very limited resources and there is very limited construction materials and where other mechanical or electrical materials because of it's not easy access. Still it is development is going on. The other countries are aiding to that particular nation, but still it is developing. The real world examples are highlighting the applications of the principle in the cyclone prone areas. These four principles the consulting engineers are considering also the home affairs countries, which is supporting to the Pacific Islands. So these four key factors are they considering they adopt. Then policy and planning. This is a resilient infrastructure. There is some key plannings out there. That is the integration of resilience into planning, then stakeholders collaboration, then climate adaptive strategies. The main thing, the integration of resilience into the planning, the incorporating the cyclone resilient designs in the urban and rural development plans. Mandatory building codes for the cyclone prone areas because of most of the countries in India that is having a separate there is research theories there, but in most of the Pacific Islands, it's not that much. There's nothing developed actually. But the thing is, they should be developed the building codes for the cyclone-prone areas because not every island is not affecting the cyclone, but some islands are there. Then yearly, they're frequently affecting. That is like, for example, you can say the Vanuatu and the Fiji, then American Samoa and South New Zealand, and as well as the Solomon Islands. Solomon Islands is some parts. They are in yearly frequently affected by the cyclone. So in that particular countries, they will not construct any reinforced RCC buildings and RCC houses. Nothing. Only the port and harbors will be in the RCC. Rest of all the houses and government buildings will be constructed in wooden structure, not in concrete structure. So, because they already analyzed it, which was this, some countries already it's there, the severe earthquake regions and as well as cyclone prone areas. So these countries already adopted. For example, the cyclone resilient policies adopted in Fiji. Fiji having the building code, but still is not developed, but currently is under developing. Then American Samoa's, the National Adoption Program of Action. They having the policies which is supporting by the Australian government for this American Samoa. There's stakeholder collaboration. So in this, some countries that need to be change the policies. They need to be collaborate with the local governments and NGOs, the private sectors and local communities. Then particularly the public-private partnership, the PPP. They're having the separate planning and they have the separate funding methods. They can lease around 20 years. They may be develop. They're having the own rules and regulations, and they may have their own designs. For example, like build operation transfer BOT, and these are all projects will be still it is undergoing in the these are Pacific Islands, but not that much. It's still under currently developing. Then climate adaptive strategies, that land use zoning to prevent construction on high risk areas, then sustainable coastal management and erosion control practices. That is sustainable coastal management and erosion control is still currently some research is going on because of that is most of the breakwater structures like a cuboid. It was developed to protect the coastal areas. For example, I can say the Kiribati. The Kiribati is the first sun rising country in the Pacific Islands. In that country, currently it was predicted in another 30 years that country will be completely submerged into the sea. So This all the people are now they started evacuated from the country. Some countries are giving the helping hands. The thing is, Australia's agreed to take the 50 peoples yearly from the Kiribati and New Zealand promised to take around 20 people from the country because in another 30 years that country will be completely submerged into the sea. That is very small island. That name is Kiribati. So in this country is severely every year severely affecting by the cyclone and the earthquake, then climate change and sea level rising. So they adopt a lot of erosion control practices over the islands, but everything's failed because of the intensity of the cyclone is every year something's changing because of the structure, then sea conditions. That is the Kiribati is in another name is known as coral rocks. There is a huge environmental impact is there. That's why most of the projects is means cancelled by the Commonwealth of Australia because of there is coral rocks and lot of sea environment will be severely affected. That's why they just stopped the feasibility study of the around the Kiribati. So, but the only thing is they identified this country will be no longer after 30 years. That's very sad news because of due to the sea level rising and frequent cyclone were affecting that area. So these are all the climate adaptive strategies we need to follow. The policy has to need to make by the local government and other countries give the helping hands to develop the aids for that particular country. The key features of the cyclone resilient infrastructures, elevator structures, then wind resistant designs and flood proofing mechanisms and local materials. The elevator structures mostly nowadays they are adopting like bridges, port and harbor structures, then wooden housing structures. Because of most of these islands are in mountain regions, hilly regions. So the elevator structures always escape from the cyclone resilient. Why? Because there is no that much flood in that area. Because it will, but one thing is there is a severe wind. Wind will be always minimum at least a normal wet season in dry condition. So in these cases, minimum we can expect around 40 to 50 kilometer per hour wind always in Pacific regions because that is a tropical weather condition always. The wind resistant designs nowadays, the many countries are giving the aiding for the developing the wind turbines. They are just supporting for the wind resistant design mechanism, which is like windmill and then the ocean energy. This all they're supporting for that. Then flood proofing mechanisms for extending the rivers and removing the river shoals because it should be the free flow of water. So there is that hydropower electrical dams they are constructing, particularly in the flooding mechanism, the flood proofing in the rivers. So these are all helping for to control the flood during the cyclone season. The cyclone season starting from usually in Pacific countries, so from June to up to the next year of April. So local materials, usually you can see if someone is like to be visiting the Pacific Islands, so you can see most of the structures, around 95% of the structures was built in wooden structures. Because of these countries are frequently affecting by the cyclones. You can see in the United States, some parts, they may be constructed in houses in wooden structures. So these mechanisms is very surprising because of it was resisting the wind. Even if it is damaged, they can construct very easily in nesting. In concrete structures, not like that because of what happened. Erosion, the sea erosion, the river erosion, continuously rain. This is even the rain is recording, the rainfall is recording around 120 centimeter, even 2-3 hours. It's very severe rainfall we can expect in the Pacific regions. This is case study, the Fiji cyclone resilient housing, how they are planning and constructing the houses due to the cyclone conditions. There's the main background is that Fiji has a historically vulnerable to severe cyclone, such as Cyclone Winston in 2016. This is, I think maybe many of the persons can know this cyclone Vincent's very severe cyclone storm, which is damaged completely the country because severely affected, which has caused widespread destructions. Even the government secretariat is completely damaged. The Australian New Zealand government was aided and it was redeveloped the nation. The design features is hulls built with the reinforced concrete frames and cyclone-resistant roofs. You can cyclone-resistant roofs. It is completely different because the design is completely because they're having uh, the reinforced bolts and nuts which was connected to the up to the foundation. The design is completely different. The elevated foundations they mitigate mainly this thing. The elevated foundations to mitigate flood risks, use of locally available materials to reduce costs and ensure cultural appropriation. Because of once the cyclone crossed or any destructions happened over this country, the inflations will be higher. Then after that, currency will be reduced. Then this type of other developing nations will be give the hands to redevelop the countries. So because if we are ordering any materials or in a procurement team, it is very difficult to get the material because it will take around 30 to 40 days to reach the material if you order in Australia or New Zealand in other countries because of this is completely in remote location. So that's the main key thing that we need to be considered. So most of the countries are using the locally available materials. In some very exceptional cases, they are asking the help to the other countries to redevelop. So the community involvement is the training program for the local builders and engineers. Most of the countries they having their own universities. In some countries they are sending the personal training to other countries. Like in some Pacific countries are sending their engineering teams to India and Singapore and as well as Papua New Guinea and the New Zealand, Australia. Still, we are also giving some training over the personals who are all coming from the Pacific Islands because they may need to know how to sustain the countries and how to sustain the resilient. So the main benefits is the workshop to educate resilient, the maintenance and emergency preparedness. They need to know these are all key benefits while they are giving the training. Then in structural part that the significant reduction in the structural damage during the subsequent cyclones and the increased community confidence and safety. So this may be enhanced in society together. So the enhancing long-term economic resilience by reducing rebuilding cost. Some buildings they may be considered reinforcing structures, but this is not a cost effective to the country. So most of them they are deforesting and constructing the house in the wooden structures. So you can understanding that tide levels in the ocean. So this is related to the cyclone resilient structure. You can see the charted data, which is mean sea water. Usually the structures, usually in India, except in offshore regions, in land structures, that everyone know that we are considering the mean sea level to construct any structure. But in the Pacific Islands, most of the structures will be constructed using a chart data. That is, the chart data is built in over the shore areas, even the old nations, but in land structure countries, usually they will be considered as a mean sea level. So you can see in the tide levels and chart data, usually nowadays all the structures is constructing from charted elevation. You can see the charted elevation. In this charted elevation, from at least 4 to 5 meters, you can see the chart data. It is mean sea water. This mean sea level, mean highest water level, means highest water level in the spring as well as in May. That is two differences there. This is the spring range, the sea surface, which means very highest factor is the highest high water level, which is considered lost over 50 years. There may be decide the highest water level in the near to the countries and near to the construction area. From that, they may be consider the storm surge, that is cyclone. Lost 20 years data, the cyclone is during the cyclone, the maximum wave height, that's called as a storm surge. From there to, they may be considered the design 5 meters or 8 to 10 meters. That's the top level of the slab or the port and harbor structures. From that is, they are considering as a chart datum. From, for example, +5 or +6, from chart datum, they may be considered for minimum depth. That is the lowest astronomical tide. That is a chart datum. Lowest astronomical tide is whichever the shore areas or islands, they may be experienced, which is the lowest tide. And the high tide is which was highest tide in the past 20 years. This data will be available in the local meteorological department or in the local defense administration. They may be give the data, so the engineers may can use this data. Then they'll be considered for the design and for the construction. This usually we are usually using in the marine structures. So the engineering innovations, the advanced materials, we need to overcome from this issue. We need to use some advanced material like reinforced concrete, polymer composites. In some countries, the reinforced concrete may not be adopted because of this cost effective. Okay. Then smart technologies like IoT based monitoring systems, then nature based solutions, for example, mangroves and coral reefs. So these are all productions will be helpful to overcome this cyclone prone areas. Then another key thing is the role of renewable energy. These resilient energy systems are very critical for the cyclone prone regions to maintain power during and after extreme weather events. Then, for example, the solar microgrids provide decentralized energy solutions, can be quickly restored post cyclones. Most of the Pacific countries, they don't have the thermal power plant or hydroelectric station. They are now using the solar microgrids. Very in rare cases for Fiji, in some other islands, they are using the wind turbine. In solar microgrids, example, the community-based microgrids in rural Pacific islands, then the wind turbines designed to withstand high wind speed, offshore options, depending on geographic conditions. In Solomon Islands, there is no wind turbines. In Fiji, they may having the wind turbine, and American Samoa having the wind turbine. The New Zealand, Australia, they usually having the wind turbines. Then energy storage system. This is nowadays is very critical in the Pacific Islands. Importance of battery storage for the backup power. Examples of the resilient storage system, example lithium ion flow batteries, then hybrid systems combining solar, wind, and conversion system for enhanced reliability. Example, hybrid energy solutions in cyclone recovery regions. So still some innovations is going on by the Australian government. And we also, the Mecanol was already developed some systems and studied some feasibilities in the Pacific Islands. That even I'm the part of that hybrid systems they're developing. So that we are searching the feasibilities and because of even if you're taking any one island, there is around thousands of islands will be there. Around only 10 to 15 islands the people can able to may live, but rest of the islands is completely ecosystem that is completely surrounded by the coral rocks. So these areas is completely prohibited for the development because of due to the economic ecological condition, the environmental impact, because the environmental impact assessment is done by the government. So it's completely prohibited for the development of some islands. The key benefits is reduces dependency on fossil fuels, ensures power availability for the critical services like hospital and communications. Main thing is usually even sometimes the cyclone times, due to higher wind speed, some power disconnection is very usual in the Pacific Islands. So in these cases, every hospitals and every government buildings, they having their own power generations like solar. They are using at present. They are using only solar. In very some islands, they are using wind turbines, windmills. So ocean energy, ocean turbines out there in Fiji. In Pacific Islands, only Fiji using the ocean turbines. The coastal defense mechanism, seawall construction, breakwaters, shore protection projects. because of nowadays it was very key developing. In some countries, they already wanted the sea level rising due to the cyclone, some severe erosion. They are constructing the sea walls, different type of breakwaters like rayons, like a cuboid breakwaters. Then shore protection projects are very vast projects going on in the Pacific Islands. Only that Asian Development Bank is funding to develop the shore protection measures. So many projects are going on Pacific these islands. So water sanitation infrastructure, the cyclone-proof water tanks, that is wastewater treatment systems, then emergency water supply network. This emergency water supply network is still currently under developing in the Pacific nations because there is a lot of study that considering there is no proper access to develop the water supply networks. Nowadays, there's some countries where this funding to develop the water supply networks, particularly in underwater using the HDP pipe and boring under the underground. And then they are supplying the water during the cyclone time. Also, still they are supplying water. Still, some countries are developing currently. The transportation resilience, elevator roads and durable bridges, improved drainage system. The elevator roads still currently developing. These are some key points that we need to consider. The engineers need to be consider the cyclone resilience prone areas, the elevator roads and durable bridges and improved drainage systems. Then communication systems. This is a main key issue in the Pacific Islands because of sometime the radio signal may not work due to the condition. Then already communication towers are there, but due to the cyclone time, it was completely damaged. Now they are rebuilding. But the backup satellite systems now this working. The Tesla company is already the Starlink. The Starlinks already give the hands to the Pacific Islands for developing the satellite system. Still, in all the Pacific Islands nowadays, they are using the Starlink for the internet as well as in the network. Even though mobile network commission, the communication towers still sometimes may be damaged with the cyclone time. So most of the people are using satellite phones. Then community alert system, the countries are developing this local radio signals. Sometimes what they may be announced, they may be raise the flag hoist in the tower that everyone can see some cyclone was formed in the sea. So these are all very easy communication to the people. It will be reach very easy to the people to protect the lives. The education and training. Currently, India, Singapore, and Australia, and Southeast Asia, some of the countries were giving the hands for the education and training to supporting the countries for developing and overcome from these issues. Workshops, they're conducting workshops like symposiums, and they're connecting conference. These are the things they are developing. And in some countries, they're giving the education training for the local engineers and incorporating resilience into the educational curriculum. It's very compulsory in the South Pacific universities and Auckland University. They developed a separate curriculum to educate the overcome from these issues from cyclones and earthquakes. Funding resilient infrastructure. Some the international organization, for example, the World Bank and Asian Development Bank and United Nations Development, this some banks are they supporting still for the developing these countries, but these countries are not receiving that much fund. Then public-private partnerships giving the good hand currently in the nations, which is very in the downtime of the people during the cyclone time. Then innovative financing models, for example, green bonds, which is nowadays all the countries have started using the green bonds because of due to the funding, because of not all the not all the banks will not support it due to this time. So what they are planning, the government is the innovative ideas for agreeing the green bonds. The community involvement. The involvement is mainly whatever the engineers are developing, mainly the community involvement is very important, and their support is very highly important for develop for the local knowledge and education training, community-driven designs, ensuring the gender and disability. Even in the most of the Pacific Islands are very severe during the diseases during the cyclone seasons. For example, malaria, dengue. And during this season, this will be spread very easily and develop. So we need to that ensuring all the thing is we need to ensure that the disability peoples and genders need to be safer side. This is a case study is a very important. The cyclone pumps impact and recovery in Vanuatu. This is very severe cyclone, the category 5, which was severely affected in 2015. The cyclone PAM. This cyclone was developed in March 6 up to March 20. It was crossed over the nation in 2015. The affected areas mainly Vanuatu. This Vanuatu and other areas like the Solomon Islands, Tuvalu, and New Zealand. This is very big cyclone, very severe cyclone that is a 250 kilometer per hour. It's very severe cyclonic storm. So the pressure is 896 bar. The damage was estimated 692 million US dollars. The death was estimated. It is the approximate death. It's not confirmed. It is 15 fatalities. That the main thing, the cyclone pump was one of the most intense tropical cyclones recorded in the southern hemisphere. It's caused widespread devastation, especially in Vanuatu, and destroying homes, infrastructure, crops, bridges. The one big bridge was fall down. Very severe, the 250 kilometer per hour. It was sustained more than 2 days. It's even if the cyclone it was developed even 250 kilometer per hour, even some cases were experiencing within 6 hours, 7 hours they may cross the land. But these cyclones, it was sustained with this more than 48 hours in the sea. So this is very namely PAM cyclone is very very dangerous cyclone. It was recorded in around 4 countries such as Solomon Islands, Tuvalu, New Zealand, and mainly in Vanuatu. Then another case that is cyclone Winston impact. This is a very severe tropical cyclone. It was category 5 in Pacific Islands. It was developed in February 7 to 24 in 2016. So this cyclone Winston was it was impacted the Fiji Island. It was record-breaking landfall because of it was near shore. Around 4 days it was near shore. The February 20th, it was around 20 nautical miles upward the land to sea, but around 4 days it was maintaining the same wind speed in the sea. And after 24th, it was across the land. It was record-breaking landfall. So in other areas, due to this cyclone, the Tonga and Vanuatu valleys and Futuna, this area is very severely affected in the Pacific Islands. Why I was taken mainly the case study from the Pacific Islands, the people and the engineers and need to know how the cyclones it was forming in the tropical regions, the Pacific regions. So it is very severely impact. Even in India, most of the cyclones will be cross in landfall around maybe the 120 to 170. Sometime in Visakhapatnam, it was recorded around 210 kilometers per hour. But in the Pacific regions, is entirely different. It's entirely different because minimum at least it may be landfall around 210 kilometer per hour to 250 kilometer per hour, sometimes 280. For this cyclone, Winston is 280 kilometer per hour. So these are all very cyclone prone areas which is redeveloping, and some research is still is going on to develop this nation to overcome the cyclone prone areas. The cyclone Winston, the pressure is 884 bar. It was very lowest recorded in the southern hemisphere. Then the damage was around 1.4 billion US dollars. The death was around 44 confirmed fatalities. Then the cyclone Winston was the strongest cyclone to make landfall in Fiji's recorded history. It's flattened villages and displaced tens of thousands of people and caused very severe economic and social disruptions. Even India was supported and the Australian government supported and New Zealand government supported to overcome the this very severe destruction in the Fiji regions. In the cyclone-prone areas, the main key role of the government is the national policy. Still, some countries they are revising the policies for the resilience, and even some PPP, the public-private partnerships, investment and disaster reduction. But nowadays is very less for the investment and disaster risk, and the coordination with the international bodies like some United Nations, some bodies are still supporting for the resilience infrastructure. Even some associations like Institution of Civil Engineers are still giving the hands and doing some research studies in that coordination with the local government of the Pacific regions and the Atlantic regions. Then lessons from the other regions, mainly from Hurricane Katrina in United States and Typhoon Haiyan Philippines, and Cyclone Amphan, India and Bangladesh is very severely affected. The Hurricane Katrina is very severe flooding and extensive property damage. The key resilience measure is the improved levee systems and community relocation program and updated flood management plans. These are the key things which was implemented in the Hurricane Katrina in the United States. Then Typhoon Haiyan in Philippines, it was very severe. In fact, one of the strongest recorded typhoons in the Southeast Asia regions. The massive casualties and displacement. The key resilient measure is the early warning system and improved evacuation protocols and a disaster resilient housing. Because of these countries already know this cyclone is going to be land for particular this location with this much wind speed will be there. So they're having some early warning systems, how they are going to be prepared to protect the countries. Because of this early warning system is very much good case study for the engineers, which will be revise the systems and mainly for design engineers how to improve the designs. That's particularly for the research engineers too. Then Cyclone Amphan, this was landfall in India and Bangladesh. That impacted significant damage to the coastal infrastructures and agricultures. And the resilient measure is very surprising. Coastal opposition and reinforced embankments and improved cyclone shelters. Because of, compared to other countries, India having the most cyclone shelters and the embankments like geotube embankments, like shore protections, geotube embankments like sheet pile with the gap in boxes. These are very good developments in India and Bangladesh waters. It is a key thing. It will reducing the risk. The nature-based solution, we having very artificial-based solutions, but that is some nature-based solutions, mangroves and coral reefs. Then ecosystems restoration projects, because wherever the mangroves are not there and coral reefs already been somewhere the people was taken out in that particular area, there is some projects is going on the ecosystem restoration. Even I'm also one of the part of this project, ecosystem restoration projects in the Solomon Islands. Then cost effectiveness and natural barriers, because of there is some cuboids will be there, there is some artificial coral rocks and will be there, so we can place over this. At least it will not 100% reduce the risk, at least it will be help the hands to reduce the risk. Then engineering standards and guidelines, there is an international standards will be that's ISO 37123. The sustainable cities and communities provide a framework for the resilience. So this code is that we are using in Australia and New Zealand, ISO 37123. This code is very popular. Still, we are using for the designs as well as making the feasibility and detailed project report for the resilient infrastructure. The national adaptations is modifying international standards to suit the local conditions such as climate, material availability, and economic constraints. Because still the Pacific Islands following the British standards and some local research papers. Still, it should be revised based on the local conditions and local availability conditions and local climates. The key considerations: wind load calculation for the extreme event, flood resistant building designs, and incorporating elevated foundations and drainage system. These are the key things that we need to be re-armored in the codal provisions and local standards, and structural reinforcement techniques for the critical infrastructure like hospitals and schools. Then capacity buildings, we need to train the local engineers and contractors to adhere to these standards, because most of the standards is not included, because every year that they are recording different category of the cyclones. and earthquakes. Even earthquake also something they predicted, but cyclones we cannot predict because of this is unpredicted. The cyclone is completely unpredicted. We can predict the landfall areas, but we cannot predict the wind speed. So continuous improvement is required. They're regularly updating the standards based on the new research and technology advancement and lessons learned from the least recent cyclone events. Because most of the coded provisions having lost past 20 years data. Based on that, only the engineers are designing and concerned was advising. But they should consider the latest cyclone events and which was learned by recent events and as well as in the new research. And risk assessment tools. So this is a key important which we need to be the risk in the construction industries. The risk assessment is very key factor before proposing a feasibility studies or detailed project report. The main thing is hazard mapping. So we need to identify the areas most likely to be affected by the cyclones. So vulnerability assessment, evaluating how the infrastructure and communities might be impacted. Then assessing the financial implications of different resilience measures, just playing the vital role for the mapping and analyzing spatial data for informed decisions making. Then modeling, predicting potential cyclonic impacts based on the different variables. That application is main thing, the prioritizing investment in the high risk zones, developing targeted mitigation strategies, informing disaster management response plans. For examples, the case examples, use of GIS in the Pacific Islands or in India to plan evacuation routes and shelter locations. This risk assessment tool is a very key thing, supplying the vital role for the precautionary measures. Then technological innovations in nowadays, the past 20 years different, nowadays completely is very, we are in pretty technological innovations world. We can use the drones for the damage assessment. Even in some areas, wherever there is no access, we can use the drone. Rapid aerial surveys, the post-cyclone identifications of inaccessible damage areas where there is no access. We can use artificial intelligence for analytics, forecasting cyclone impacts, optimizing resource allocation for evacuation and recovery, then ensuring accountability in disaster relief funds, particularly the facilitating decentralized and secure transactions. Then IoT based monitoring systems. This is nowadays this is very following in various regions and the real-time data collections on infrastructure conditions, integrating early warning system for protective measures. Example, Cyclone Gita. Use of drones in Tonga, the artificial intelligence based forecasting tools in Fiji. This was used in the cyclone Gita. It is near to Tonga. This Fiji and Tonga is very close to the countries, around 20 nautical miles. Is very near. The both countries is very near. So there's using drones or AI-based forecasting tools was used in Fiji to analyze the Tonga. The benefits is faster response and time improved efficiency in disaster management, enhanced resilience through data-driven insights. These are technological innovations to overcome from this issue. The key takeaways, the early warning systems, like before the slide I was explaining, the drones and the satellite systems. Then adaptive designs on the robust recovery plans. We need to, every year, if some cyclones are closer in the landfall in the Pacific regions, immediately some universities will be readily available to do the research activities because due to the cyclones, what are the impacts will be there, or some environmental changes, how the weather was, climatic condition was changed in particular regions, if any impact is very severe or not, how the sea ecologically anything affected or not, everything will be completely steady. This study is the government is funding for that because of every cyclone. The in Pilbara port in Western Australia, the past 2 weeks before it was landfall over that port, the port was severely affected. So immediately after that, the University of Queensland was sent a team to do the research. So after the research, will be re-amend the codal provisions based on the local conditions. Then international aid and collaboration, mainly many countries are aiding the Pacific Islands and Atlantic regions and Gulf regions for overcome the from the cyclone-prone areas. Then international collaboration like global partnership and regional cooperations and technical supports and funding mechanisms. For example, most of the Pacific Islands countries, World Bank and Asian Development Banks are funding, and in some countries they're giving the direct aids to the islands. So accessing expertise and training programs provided by the local developed nations and international organizations. Then funding mechanisms very common, then utilizing international funds such as Green Climate Fund, that simply we call as the GCF. The GCF fund is a Green Climate Fund to support large-scale resilience projects for developed nations. Then future trend is predictive modeling and big data. They're leveraging advanced analytics and forecast cyclone patterns and identify. Then green and sustainable materials like development of eco-friendly, durable materials designed to withstand extreme weather. Focus on modular infrastructure, rapidly deployable and adaptable structures tailored for emergency response and long-term use. In somewhat the building resilience through the participatory planning and local leadership initiatives. These are future trends they are adopting. Then incorporating the resilience into city planning to manage stormwater heat and other climate risks. Then call to actions. This is the conclusion. The invest in resilience because of most of the islands and most of the countries, they are not ready to invest to allocate resources to develop infrastructure that can withstand future cyclones. This includes funding innovative designs, retrofitting existing structures, and promoting renewable energy solutions. And then the collaborative across sectors, build partnership among governments and NGOs, private sector, public-private partnership, and local communities to share knowledge and coordinate efforts for a unified approach. Then empower local communities. This very key thing, which is currently following in the most of the countries, that provide training and tools for community-led initiatives. We need to be ensure that resilience measure align with the local needs and traditions, because of most of the local communities projects, the detailed projects are just highlighting there is no local needs, but there is some local needs will be there because some tribal peoples will be there because they want, there is no access to identify the peoples, but it should be identify and we need to adopt a solution for that particular region. Then strengthen education awareness, then foster a culture of the preparedness through education, workshops, and inclusions of the resilience concept in school curriculum. Nowadays, in most of the countries are adopting about the cyclones, but still need to redevelop the curriculum to implement the cyclone resilience infrastructure as well as the climatic change conditions. It should be implemented in the school curriculum. Thank you so much. I have very limited time. The 1 hour is not enough for me. Anyhow, I was much happy. Then I hope that everyone will be understand about a cyclone resilient infrastructure in Pacific regions, which was lesson learned from my side. So if you have any questions, yes, you are welcome.
Participation in this is the questionnaire session. Kindly send your queries or any doubts regarding the session.
Any questions, please?
Okay, Ramkumar, they may be quite interesting topic in coastal regions. How can they resilient structures is very wonderful and fantastic. I mean, one more person asked a question. You can see your chat box. Is there any
Yes, ma'am.
codal provision for designing structure in the cyclone prone region specifically? They are asking.
Yes, ma'am. There is an international standard, sir. There's the ISO. The ISO still we are this following the cyclone prone regions 310123. This code that we are using. I will share that code in the chat box soon.
Okay.
Very interesting questions because there is no such standards providing. There is not that much international standard. Only the ISO standard is having the designs.
Okay, Ramkumar. Thank you, Ramkumar. Participation, any queries? Kindly ask. Otherwise, we'll wind up the session. Yes, Ramkumar. Thank you so much for your insightful session and explain your knowledge, sharing your knowledge and experience. Wonderful section. Thank you once again. Thank you so much, Ramkumar.
Thank you so much, ma'am. Thank you so much for giving this wonderful opportunity and SSM Institute of Engineering and Technology.
Yes.
Even this is this is my great pleasure to share my valuable experience to everyone, so they can know how this resilient infrastructure will be overcome these problems.
Yes,
so I'm very much happy for this. I'm very much thank you to everyone and particularly for Selva Bharati ma'am. I have no words to say because I have something in my mind. Thank you very much for the SSM Institute.
And one more question they're asking, Ramkumar. The structure should be rigid or flexible during cyclone?
The structure is completely inflexible during the cyclone.
Okay.
Because rigid that we cannot able to follow in the coastal regions, particularly in the islands.
Okay.
Yes.
Kannan sir, kindly share the feedback for this session, sir. Participations, don't share your feedback and attendance automatically share in the Microsoft team, and the feedback also don't share your colleagues because that feedback is deciding for the providing the certificates. So kindly fill the feedback and attend the session. And Ramkumar, shall we wind the session?
Yes, ma'am. Yep.
Yes.
Yep.
Thank you so much, Ramkumar.
Yes,
And once again, thank you all the participation that actively participate in the first day FDP. I will wind up the session. Tomorrow we'll continue. Have a good day. Thank you.
Yes,
Thank you.
Thank you so much, ma'am, and thank you for all participants. Thank you so much.
Thank you.
Have a great day. Yeah.